Okay, welcome to UCLA QC Bio Collaborative Workshop 1C, Advanced Unix. No, we're up to 5, scripting and queuing for large data for spring 2025. So this is 1:30 to 4:30, next 3 days, Tuesday, Wednesday, Thursday. We'll fill all of today for sure. And then we probably won't need all 9 hours, but whether we kind of cut short early tomorrow and then kind of balance it between 2 and 3, or whether we fill up 2 and then do 3 even shorter, I'm not sure yet. But we're a small group, and we kind of have maybe some extra time, not going to fill all 9 hours. So, definitely ask questions as they come up and stuff. We have a good chance for interactivity here, and any questions you have, just ask them. Just start talking. You don't even need to raise your hand or anything. It's a small enough group. So let's see. So because you're going to need a copy of some large files, there's about 100 gigs of files you need a copy on Hoffman. While we do sort of an intro, why don't we have your computer working on the copy so that by the time we get to where we need the files, they'll already be done. So SSH into Hoffman with your Hoffman account. And on slide 19, maybe the best way is actually go to the copy and paste file. So the guy that just came in, did you get the email this morning? Got the files in this one. Okay, great. So right at the top of that file where it says slide 2, there's SSH or whatever your software is for getting on Hoffman. It doesn't matter. Get on Hoffman, run this QRSH line to get on a compute node, because you initially SSH into a login node. We need to work on a compute node. You're not supposed to do any heavy computation or IO on a login node. So here is the QRSH line to get you with a certain amount of resources on a compute node. And then hopefully you don't have to wait very long to get on your compute node. And then once you're there, you're going to copy some stuff into your Scratch directory. So if I get on my Hoffman account, so there I'm on login 2. There's a round robin or whatever. It doesn't matter which one you get on. And then here's the QRSH command. Okay. And hopefully that only takes, a few seconds or a minute there. Those resources aren't too crazy. 3 cores, 4 gig of RAM per core, 1 day for the session. Those should be fairly easily satisfiable without waiting long. Sorry? So our workshop is 3 hours. I wouldn't want to go less than 3 hours, so your session blows up while we're here. 2 hours is kind of a boundary, so we already crossed that. The next boundary is a day, so we just round up to a day. Oh, okay, so there I am. I got on node 6063. And if you haven't seen it before, hopefully your experience, about the Scratch space, right? There's uScratch. Each of us has 2 terabytes of quota down there. Of course, they delete it once in a while, which is the problem. But there's a shell variable set by the Hoffman 2 startup scripts. The Scratch shell variable should be set to your directory, your Scratch directory. For me, it's uScratch C cocos. For you, it'll be uScratch first letter of your username. That is where we want to. This one that you see on my screen. This is where you're going to copy from, but you're going to copy to your own so that you have a place where you can modify all the files and do everything, because you can't write into my place. So that just shows that this variable should be set correctly already for you. And that way, everywhere in the slides where I need to refer to your Scratch space, I can use this variable, and where I need to refer to my Scratch space, I'll just write uScratch C cocos. And so that's how everything will be kept straight. Anyway, so then change down into your Scratch space directory. So now you're in your own Scratch space. And then the CP command that you want to do to copy the files is right here. So this is a recursive copy of a big directory tree. The V will give you progress as it goes through. Each file will produce a line of progress. The I is a safety, that if you already had files that are going to collide with this destination, that would let you know, do you want to overwrite them or not. The P preserves permissions. So like execute bits on shell scripts and stuff like that will get preserved with this P option. And the source directory where everything's going to come from is in my scratch space, use scratch C Cocos workshop 1C 2025 May, day one start. And the directory we're going to put them into in your own scratch space is W1c. So get that command going, and you'll see here that it'll make progress, and that'll go for a while because I think the total size is it's close to 100 gigabytes. I think it'll take a little while. So let that churn while we have some time before that's ready, so that we can just talk about some general introduction and background and context and stuff. So, the general context is that over the last decades, computers have gotten so fast and so many resources. My personal lifetime, it's like 10 million-fold, billion-fold improvements in CPU, memory, permanent storage like disk, and so on, network speed. It's all gone up like crazy. And biology really taking advantage of that now because of high throughput DNA sequencing. That's the real application that's driving biology kind of into sort of the big data, large compute world. But unfortunately, computers have to be told in detail what to do. I mean, maybe with AI these days, it's a little easier to tell them what to do to program if you don't know programming. But in general, they have to be told in very great detail what to do. And there's different levels of ways you can try to bridge that gap. So you can use stuff like Microsoft Office, Adobe Suite, Google Docs. So these are sort of mature applications which do certain things, but you don't really have to have any technical knowledge to use those, right? They're sort of really polished and mature, and they do what they do great. You don't really need a lot of CS or background whatever to use any of these things. So that's not going to work for us, of course. Then there's sort of like compromised applications, which aren't quite as mature and well-developed as that, but a lot of academic open source work is kind of in this category. Like if you use NCBI web-based BLAST or Galaxy server, bioinformatics server, maybe you've used. So these are sort of, less polished. You need a little more from the user, but they're still like, you don't have to code to use them, right? So it's like the more wet bench biologists can do this kind of stuff and so on. So that also doesn't really work because most of you are presumably kind of bioinformatics-y people. And so that's not the level for you either. The next level is kind of like where there's not really a program that does what you want, but kind of the pieces of what you want to do already exist, and you just sort of need to glue them together. Right. And that's where like the shell is really useful for that. Right. So the standard Unix utilities also for manipulating text files and stuff like that, like cut, awk, set, and the rest, which presumably because of the, this is the advanced Unix, so you've presumably seen that stuff already in some form earlier. So now we actually have to sort of start doing some light programming, right? So that's okay. But this is sort of the level where the shell lives. And this is the first level where sort of as a bioinformatics person, you spend a lot of time at this level. Maybe the next level, so there's some shell commands and special shell characters. You're probably familiar with some of those at least. Here's a list of standard Unix utilities. You're probably familiar with some of those as well. I need to have a little bit exposed where I can put the keyboard focus back in the slide navigator. Okay, there we go. Then you get to cases where you have to actually really code, right? And so for bioinformatics, a lot of times these days that means Python. If you were older, maybe that means Perl. These are sort of lighter environments. They don't have a huge baggage inherent to them, although there are big ecosystems around them that you can get a lot of, so they're not small in a certain sense. But now you're actually coding. Next level would be stuff like R, MATLAB, Mathematic, and so on. These are more heavyweight environments that have a lot already built into them, usually a big notebook-based graphical interface and so on. Of course, Python can be done that way too, because you've got like, notebook interfaces for Python too these days. But sort of these three layers, this is sort of where a lot of bioinformatics people spend their time, right in here. At the bottom level, you've got high performance software that has to work with high resource efficiency on the machines. That's where things like C and C++, kind of hardcore computer science coding and so on like that. That is essentially the layer that's underneath everything. What is Python written in? Well, C++ and C. What is practically every environment written in at some level? What are the operating systems written in? C and C++. So that's the bottom level these days. But a lot of times there is some bioinformatics work that occurs down at that level. For example, like your BWA aligner, you know, a lot of your core utils, SAM tool, you know, a lot of the core utilities are written down there because they have to be high performance. But as sort of a day-to-day bioinformatics person, you're really doing more engineering work with existing software pieces. And so it's sort of like these three layers are kind of where it's at. So yeah, so this is kind of where bioinformatics lives. And the focus on this workshop here is going to be that bash gluing together layer with a focus towards your problems are large, meaning you've got either large files, hundreds of gigabytes maybe, um, or large numbers of files. And so you really need to be able to have some facility with the shell and so to manipulate those and impedance match them well to Hawkins so that you can run tasks on those size files of that size efficiently. Um, so just curious, are any of the copies done yet or no? Still chugging away. Okay, so we still got some more time. Okay, we got another couple slides of this intro stuff. So, you know, one of the things is that in the slides, everything that's underlined is a web link. So like this more shell link here, if you open it, you'll go to this page called Awesome Shell, which just has a lot of links to resources about the shell. And especially like these guides at the bottom, some of these are pretty good. If you're interested, you can kind of get into that, but that's sort of other resources. Um, so, you know, kind of why kind of get into shell? I mean, you have to know some shell to get anything done in the command line, and you already are kind of intermediate level already. So obviously you'd have some facility with shell already, but kind of why get more into kind of like harder core shell? Well, and the answer is still sort of like, even though you might be spending a lot of time in Python and so on, you still got to get the inputs to the program, organize the outputs. You have to manage huge collections of files and so on. And this is all more shell-like stuff and not really stuff that's so convenient to do in the environment, in like a Python environment or something. So you know, it's really sort of like the overarching glue layer of everything. And so you really kind of, when you get a high facility with the shell, it really greases the wheels for sort of everything else. It's sort of it really does make you more efficient. Um, it has a lot of features, more than you might expect. I mean, it's a full programming language, really. I mean, there's a certain size of programming problem where you don't want to do it in shell, but you can do surprisingly large amounts of shell. And the shell has some advantages. Like, for example, it hasn't changed much in 50 years. So it's very, very stable. And you may be familiar with Python and like Python package dependencies and stuff like this. Like Python breaks every other, 5 minutes, right? Especially if you're doing AI stuff. It's like the dependencies are always going out of stale or incompatibilities. And so shell hasn't changed in like decades, and it continues. It's mature. It works. It continues to work. It's also very portable. Like on Mac, if you're on a Mac, then that's BSD Unix under there. And when you open a terminal window on Mac, you're talking to like a shell on your local machine, and it's basically understands everything that we're going to talk about. So if you're on Linux, of course, you've also got this kind of stuff. If you're on Windows, I'd recommend that you get into something like Cygwin or Windows Subsystem for Linux or a virtual machine or something and get a Linux-like environment going on your Windows machine. And then you can also live in this world where everything works like this. But it's very portable. That's great. And it's often actually pretty efficient because what the shell will allow you to do is take like, say, programs that don't understand compressed files, but adapt them so that they can take compressed inputs and write compressed outputs. And that really helps you kind of work with large files because they don't have to be uncompressed on disk. You don't have to have a compressed and uncompressed copy. You can actually write the compressed version directly without an intermediate. So it helps in time and disk efficiency and all kinds of stuff. So it's a glue language with a lot of features that are relevant to getting real work done. Okay, so this workshop, like I said, we follow workshop 1A and 1B in the QC bio world, but you don't really need to specifically take in those if you have equivalent experience. The kind of stuff I expect you to have seen is kind of commands, like this, basically. This is only the second time this workshop is been given. The original time it was called Workshop 36, but it really is kind of the third part of Unix, so we renumbered it. Kind of the first pass of this was I was really kind of trying to show you like everything in Bash, and then it kind of completely out of control. Like it turns out that like even to cover just like the ways you can manipulate strings in Bash already takes like 10 slides and takes forever. So instead, what we're doing is we're going to study kind of it's also very hard to motivate it. Like, how do you can't motivate a ton of abstract features without having problems that need them. So Instead, what we're going to do is we're going to have a case study, basically. And the case study is basically inspired by workshop 6, which is our bisulfite sequencing workshop, which was just taught last week. Bisulfite sequencing is one of the applications that on campus is kind of common because a lot of PIs are interested in it. It's also a case where the aligners are pretty slow. And it's also a case where the files to be aligned are usually pretty big because like if you're doing human data, it's not like RNA-seq where like you're concentrating the reads where the genes are. Whole genome bisulfite, you have to do deep coverage on the entire genome. And the human genome is 4 gigabases and deep coverage might be 20-fold or something like that. Well, that's a lot of data. And then if you're doing a lot of samples and stuff, well, now everything gets big. So it's a great example problem that sort of illustrates what we want to show. So how do you match that to Hoffman? The main strategy is going to be basically to break up the big inputs into lots of little pieces, get all the pieces done, and then reassemble the pieces. Because Hoffman is much happier to deal with smaller jobs than it is to deal with bigger jobs. Bigger jobs, you got to wait a long time for them to start. A very small fraction of the nodes on the cluster will be eligible to, they even have the resources, RAM and cores to run a large job. And so you really just shoot yourself in the foot if you kind of try to run a small number of large jobs. It's much more efficient if the problem can be broken up that way to turn it into lots of small, like lots, hundreds, thousands, tens of thousands of small jobs and run them up on Hoffman as tiny pieces and reassemble them after than it is to do small numbers of big jobs. Now, sometimes that doesn't work. Like if you're doing de novo assembly, or if you're doing AlphaFold, the neural network-based protein folding structure prediction, those are large RAM specialized resources like GPUs for AlphaFold and so on. Those the requirements are what they are, and they can't really subdivide them. But almost all day-to-day bioinformatics problems are sort of what are called embarrassingly parallel, which means that sort of like the problem involves doing the same thing to millions of reads, tens of millions of reads, hundreds of millions of reads, billions of reads, and each read, say, or whatever the unit is, can be handled completely independently of all the others, like alignment. Alignment, knowing where a read goes, each read just goes against the reference genome, and it doesn't really matter so much where the other reads are going. It's just this read, you figure out where it goes, and that's it. And you could do that independently of all the other reads. So it's a lot of bioinformatics problems are very naturally in this world of they can be broken up into as many pieces as you want, do all the pieces independently, and then reassemble them. Okay, so we've already done this. Also, I should mention, maybe you've got the setup already, but you'll notice that when I SSH into Hoffman, I did not have to type my password, right? So I also don't know what software you're using. Some of you may be using some, if you're especially on your Windows, you'll need probably third-party software. But if you're using command line on Linux or Mac, you're probably using OpenSSH client and so on. Your command line looks like this. And you'll notice I got on when I didn't have to type a password. So that is called that's crypto-based, in this case, an RSA key pair. My computer has a little file on it that doesn't leave this computer that's called the private key. There is a file on Hoffman that is the public key corresponding to that. And my laptop, at the beginning of the SSH interaction, my laptop is able to prove that it possesses the private key without divulging the private key. And so that way my machine can prove who I am to Hoffman without kind of giving away what that is. The way that works is this is now not a remote shell. This is a shell onto my own machine. In my home directory, in the .ssh directory, there is a file called IDRSA. That is my private key. That file I can't show you that file contents, and that file stays on my machine. But on Hoffman, now this is my Hoffman window. I also have a .ssh directory in my home directory. And inside there is a file called authorized keys. And I can show you the contents of that. I have quite a few authorized keys, but the one probably that is matching my laptop is this one, because I can show you the public key on the laptop. I have both, although the laptop doesn't really need the public key, but you keep them. If you have the private key, you might as well keep the public key next to it because, I mean, they're a pair. So yeah, so this is the public half of the key, and this is the blob of text you drop into authorized keys on any machine that you say that anybody that proves that they have the private key that goes along with this is able to log in as you without further interaction. That's really nice because not only is that convenient, I can just pop open a window and just go bam, but as we'll see later, that makes scripting easier. You can script SSH. So that allows file transfers, and SSH to be scripted and stuff, and you can do kind of cool stuff with that. So anyway, I mean, how you set that up kind of varies. If during the break, we'll try to take a break every hour. So we'll take a break at 2:30 and at 3:30, either during the break or at 4:30 after we're done. If that isn't set up for you and you want to set that up, we can figure that out.
That should be your computer space. Right?
Sorry?
The authorized key should be your computer space.
So the way it works is on your local machine, you generate the key pair. So I think it's called like in OpenSSH, I think the program is called SSH keygen. And then whether it takes parameters, and if you've already made a key, maybe you don't want to overwrite. We have to be a little careful when we run keygen, but keygen will basically spit out on your local machine the two files, the private key and the public key. Then you take the public key, you SSH into Hoffman whatever way you do now, which involves a password probably. And then you put into the authorized key file on Hoffman that little blob of public key text into the authorized keys file. After you do that, then it should all just work. You have to make sure your SSH software in your local machine knows how to find the private key, which is like for OpenSSH, that tilde/.ssh directory, it knows to look in there. So if you put the private key in there called ID_RSA, it will find it automatically. If you have multiple public-private keys, there's ways to configure SSH to know how to use which key for which machine and so on. But it gets complicated in the fully general case. But it's actually only like 4 minutes to set up. It's not a big deal. If you're using Windows like PuTTY and stuff like that, it's a little more. You got to figure out where in the GUI of the terminal emulator you put in the key stuff. But they all have a way to do it. Okay, the copies should be done now. Everybody's copies are done. Yes. But you all got on compute notes pretty quick.
Yeah.
Yeah. Okay. And how about our online person? Everything going well over there?
Yeah, it's still downloading.
Okay, but you're making progress.
Yes. Yes.
Okay, great. All right. We can talk about a few more things while that's still going. Word Microsoft software wants to update. Let's get rid of that. Okay, mine's still going too, I guess. Oh well. All right. It really is. It really is a big set of files. Okay. I should mention that there are more than one shell in the world. The original shell was called Bourne shell, just sh. There's bash, which is the Bourne again shell. There's the C shell. There's the T shell, CSH, TSH. There's the corn shell. There's Z shell, and so on. On Hoffman, you should be getting bash as the default. And some of the stuff we do in the whole workshop are probably bash specific, possibly even a recent bash specific, like bash version 4 or something, to find out what shell you're talking to. So like, okay, so here's my local machine. Here is Hoffman. I guess I don't have that Hoffman window is busy doing the copy. Let me get another Hoffman going. Notice, of course, you can have multiple sessions open to Hoffman. That's no big deal. You can find out what shell you're talking to with PS $$. We can explain later how that works, but basically you see that I am talking to a bash here. On my local machine, what am I talking to? I'm also talking to a bash. Actually, I think recent Mac OS's default these days to Z shell. So you might see that, but I think I've changed my Mac back to the old default it used to have, which was bash, because I've been using bash for many years, so it's kind of my thing. Now, among all these shells, they all share a huge amount of core functionality, but when you get into kind of like the most fancy features, there's a little bit of syntax differences and stuff, and so then it kind of matters. Sorry? So like fancy features, like pretty fancy features. Like we might hit the outer edge of them at some point. If I remember, I might mention it or something, but it's easier to just say always use bash. I mean, it's pretty much always installed everywhere. It's got all the features we need. One of the things, like some people get like really into their shell and like super customize it and stuff. So like, I think if you search for like, oh my ZSH or something, like if you're a ZSH person, there's like whole repositories of like hundreds of themes and customized modules and crap, and some people get really into decorating their shell with all kinds of stuff, and if that appeals to you, you can go and chase some of that. But
Those are cosmetic.
so
Those are cosmetic.
cosmetic,
Cosmetic.
they're mostly cosmetic, yeah. But it depends. I mean, some people are like in doing like managing large software repositories and they're doing Git all day, every day. And like then they get super fancy shell prompts that show them like the current, all the state relative to their Git, situation or whatever. So it depends on what you're doing and so on. I am pretty happy. I mean, I've been doing bioinformatics for 20 years, more than 20 years, and I'm very happy with sort of the stock. My terminal is sort of the stock OS X terminal. My shell setup is pretty much stock. My text editor is TextEdit on Mac OS 10. I'm pretty happy with the stock setup. It's done me pretty well. But some people really like to customize their text editor and whatever. It's just I mean, the advantage of customization, you can really make things like you want, and you can make yourself a little more efficient. The disadvantage is that it becomes very not portable. As soon as you're on somebody else's machine or trying to explain something or whatever, well, now none of your environment is over on the other side. So there's a hit that way. So it's a trade-off. Sorry. Okay, great. We've got our first copies finished. In fact, you beat me, right? So this one's still working. Oh, and then if you actually care about what version of Bash, this is the thing to ask. So that will tell you, oops, that's not the right window because that one's busy. Here we go. So on Hoffman, it looks like I'm in the 4 series, 4.2 something, whatever. Actually, on the Mac, I'm on the 3 series. That's because Apple really is sort of behind on all open source software as part of the core operating system. So it's also related to licensing. Apple is not a big fan of GPL and so on and whatever. So this is an older bash on this machine. I think if you're into Mac OS, I recommend Homebrew. And on this machine, I think in Homebrew, I've got a more recent bash. And then like in Homebrew, the bash I have is a oh, that's not, I didn't get the syntax right there. There we go. That's actually a 5 series on the Homebrew bash or whatever. But I think Hoffman should default to bash 4, and that's basically the level I'll assume kind of in the workshop. There's just a few edge cases that I think, like bash 3 is a little older and like some things don't work quite the same. So this doesn't really matter right now, but some of like the brace expansions I think were updated in bash 4. So like this is now on my local machine a bash 3. So I don't think bash 3 understood leading zeros in brace expansions. So here you see it preserved the leading zeros. The older bash did not. So that's like there's an example of a shell version difference, right? So, but it's sort of like pretty specialized features that where the differences lie. I don't want to get too bogged down into this, but sorry. Oh, you're done copying too. Great. Okay, so copies are finishing. Why is mine not finishing?
Mine is done as well.
Okay, great. We got 3 done. We just need 1 more and my own. Or did I scroll my window? No. I thought I might have scrolled up a little and missed the ending, but no, there's the bottom and it's not done yet. Okay, we can do a little more exploration while that's still going. One of the things that's important to know is the distribution of what kind of nodes are on Hoffman. How many CPU?
Yours is done as well now.
Oh, great, thank you. And so how about our last guy? We done? Not done. Okay, you're the last one. But you should be almost done, I expect. So we'll do this next little bit and then we should be basically ready to go. So one of the things that's very interesting, good to know when you start dealing with large jobs in Hoffman is what Hoffman looks like as a whole in terms of how many nodes are there, what kind of cores are on, how many cores per node, how much RAM per node, stuff like that. We'd like to know that distribution because that helps us decide what kind of resources we're going to target with our pieces when we break things into pieces. So let's investigate a little bit that. So like the bottom half of this slide and the next slide are talking about that distribution. The top bit of this slide is just to remind us what your limits are. So some of the things that are relevant, if you type ID, that should tell you what groups you're a member of on Hoffman. So my user ID is 9271 Cocos. My primary group that I belong to is Mateo P. my PI basically. But then you see I'm also in the group MCDB. So those are the groups that I belong to on Hoffman. You may belong to multiple groups or just one. I don't know. Groups, so people, some research groups buy into Hoffman and they contribute hardware nodes, or they buy storage space. You can buy storage space on Hoffman in 1 terabyte increments that are renewable yearly. And if you're part of a group that's bought stuff, then you should be in a group membership that gives you access to those resources. This is how to see what quotas you have on various piles of storage space. You can try my quota. That should show you your group's quotas. So for example, this MCDB group that I'm in is 13 terabytes of space. And this is a very typical situation for shared storage. It's 99.4% full because nobody ever deletes anything. Right? And as soon as somebody deletes something, somebody fills it up again. And so this is why I kind of, and you may also be in the situation, scratch space is your friend, right? Because scratch space, although it's not paid for and it goes away every once in a while, like hopefully you get the emails once a quarter or whatever, and they say, whoa, it's the Hoffman fall update or whatever, we're resetting Scratch, it's all going to go away. Hopefully you save stuff before that goes away. I have people in our research group that have lost a quarter's worth of work because they forgot that Scratch was going away at a given moment. So yeah, so this is the problem with shared space often, is that it's never enough. It's always full. People rarely delete things. If you're in a luxury, if you're in a luxury situation, maybe your group actually has enough space and it's not full and you can actually do real work in there. And that's great if that's true. But for a lot of us, this is our situation with our group storage. So then this command will show you your quotas in the other places. The two main other places where you have space are, that command shouldn't take too long. Oh, come on. It's probably because I'm doing this on the login node. I might have more success doing that on the compute node. Yeah, the compute node was faster. The login, somebody's doing something on the login node and the login node's bogging down. So I'm going to abandon this session. We don't need it anymore because our copy is done now. So this is our copy just finished. And here is my quotas. The quotas will be the same on all the nodes of Hoffman. It's just that the login node is bogged down right now. So we'll just forget it, doing it there. But your two main piles that you have here should be your home directory and the scratch space. Home directory, it looks like the quotas right now are like what, like 60 gigs or something, or 60 megs, not gigs, right? Tiny. Home directory is not worth much. The bigger space is the scratch space here, where here's the limit, 1863G. That's probably because quota is reporting binary gigabytes. There's always this question in computers whether things are measured in powers of 2 or powers of 10. 2 to the power 10 is 1024, very close to 1000, very close to the kilobase metric prefix, 1000. So oftentimes 2 to the power 10, 20, 30, 40, kilobase, megabase, gigabase, terabase is, people abbreviate KMGT, but KMGT for science people, which you're kind of also, because you're in biology department or whatever, KMGT in the metric system is 1,000, million, billion, trillion, and those are not the same. They're like 10% off by the time you get to terabytes, right? Because it's like 1024 over 1,000 to the power 1, 2, 3, 4, 5. It's a ratio above 1 that kind of grows exponentially eventually, and so by terabytes it's like 10% off. So there's always this question. So does the G mean, and people even pronounce them differently. Sometimes people reserve gigabytes for the decimal version and gibibytes for the binary version or whatever. Anyway, I think what this is that quota is displaying this answer in gibibytes, but the Hoffman administrators have given you 2 terabytes decimal. So I'm sure if we multiply this out, where's my calculator here? So if you take like 1863, and if it's displaying gibibytes, so that's mebibytes, that's kibibytes. I hit some key. Okay, there's 1024, that's a K times 1024, that's an M, 1024, that's a G. For some reason, finger is brushing like another key or something. Let's try that again. Times 1024, times 1024, times 1024. There we go. So that's, if you multiply it out, assuming that that's 1863 gigabytes, that's what it is in decimal, and that's pretty close to 2 terabytes decimal, which is probably what the administrators actually specified. So anyway, it's not really here or there, but it just explains that. But anyway, this is, for a lot of us, this is our main pile.
If you are part of different groups, you'll still have one scratch.
Yeah. I have heard stories of people with strong enough motivation that have convinced the administrators to give them more scratch space, but it's like all on a case by case. You got to make your case and argue for it and so on. There are definitely times when 2 terabytes is not enough. If you're doing AlphaFold, not enough. It's like more than a terabyte just to download the databases. If you are doing large bisulfite analysis with multiple samples, that 2 terabytes will go really fast. So often what that means is, for a lot of us, Hoffman is not a great place to permanently store stuff. Just, you don't have the space. You have either some cloud-based network storage that your group controls or you personally control, or external USB hard drives or something, but you have storage outside Hoffman. Your mode of interacting with Hoffman is like, to do a project, you take your external storage big space, you copy the relevant parts you need to scratch space on Hoffman, you operate upon the stuff on Hoffman, and then when you get your analysis products on Hoffman, you copy them back out of the scratch space to your outside big pile of storage. And that's the data flow you kind of do all the time. So for a lot of us, that is the way we end up interacting with Hoffman with large data. Like I say, if you're in kind of an luxury situation and your group has actually bought sufficient space in the project directory and it's not full, you can do your work in Hoffman and leave it there in the project space and so on. That's more convenient, but it's just not practical for a lot of groups because buying that much storage on Hoffman is expensive.
Can you compute from your storage space if you're
No. Hoffman has always resisted any attempt to make external types of storage look like they're part of the Hoffman file system. So there's no seamless integration of external space into Hoffman. There are command line tools like rclone and stuff that will help you move stuff between cloud-based external storage and Hoffman. There's also the Globus business. You can also run rsync on your local machine if it's just ordinary files that, like an external USB disk or something. Anyway, there are tools to help you with that, but that's not seamless. Okay, so, and then my resources talks about the queue situation. So there we go. Oh, that was actually longer output than I thought. Anyway, so it says you're in the group MCDB. MCDB has contributed nodes to Hoffman. So actually I have what's called high P access to the nodes that our group has bought. Those nodes are these 5 nodes. These are the stats of what those nodes are, how many cores, memory, and so on. It'd make a little more sense if I made this wider. So it's like there's a 192 gig, 292 gig nodes, 264 gig RAM nodes. Cores are 20, the big guys have 36 cores. The smaller guys have 16 and 24. And then these, which are hard to read, but these basically encode limits on how you're allowed to interact with the Hoffman job queue. So it says, like, in certain queues, like I'm limited to what are called 100 slots. That's basically like 100 cores you can think of. I'm allowed to use out of this MCDB pod queue. For the system globally, I can have 500 jobs in the queue at a time, but that's my limit. Okay. That will become a problem. And when we get to day 3 job arrays, I will tell you how to get around this limit, because my job array limit is 75,000 jobs, but my ordinary job limit is 500 jobs. And so one of the things we have to talk about, and that's the topic of day 3, is how do I stop using ordinary jobs and start using array jobs? Because this is where you're allowed to submit really large numbers of jobs. Yes, there are. If I didn't really talk about it when we did quotas, but the quotas are not only on total space, but on number of files. But for most people, the number of files limit is not as big of a problem. So like you see here, files, quota. So this is space quota limit. This is files quota limit. So this is the 2 terabytes of space. And you see in the scratch space, I have the 0 means none, basically. So in the scratch space, actually, I can create as many files as I want. But in my home directory, I have not only a 60 meg limit, I have a 5 million file limit. But you're not likely, that's 5,000 K, that's 5M. It's not likely to, I'm at 40, right now I'm at 42,000 files, right? So like I said, most people don't have a problem with the file count limit. Although I have heard of people that hit it, making tons and tons of very small files, but that's a bad idea for a lot of reasons. Maybe on the project space, does that have a low file? Well, even there in my project space, there are 70,000 files and the quota is 13 million. Yeah, so actually, so this is the 99% space usage. We have 21%. Oh, actually, I am using 70,000 files, but the entire group is using 27.5 million files. So actually, the entire group is at 21% of the file quota. But we're basically full on space, so it doesn't really matter. But yes, the quotas are in both, in full generally are in both space and number of files. Okay, let's look at the node distribution. And I'm going to use R to do that because one of the cooler commands that you probably don't know on Hoffman is qhost. That's going to produce a lot of output. Scroll by, so I'm going to pipe that to less so that we can see it. That is a list of all the nodes on Hoffman and their most important characteristics, including memory total. Like this is a 256 gig RAM. There's a little bit. It's like this is really a 256 gig physical RAM machine, but there's a little bit because of overhead and whatnot. So it comes out as 251.7 in this list, but this is surely physically a 256 gig RAM machine because RAM only comes in binary sizes, basically. So, and this G is probably a binary G and not a decimal G. But anyway, and this is how many cores it has. I would actually consider that a more important number than threads because this is with hyper-threading, which never works that great. So this is really how many physical cores there are. They can pretend to be 32 cores, but there's really 16 real cores in this machine. And this is the host name, stuff like that. Anyway, that's the key stats you need to sort of understand the distribution of nodes on Hoffman. And I'm going to import that into R so we can make some little quick tables and histograms. I don't expect you to be an R person. Maybe you are or not, but all we care about is the distribution that comes out and not actually getting this code to run for you. But this is one of the cases where I'm going to have use SSH in a scripting form. Because if I give on my local machine this SSH command, you may not know that after you give your user at host, you can actually put a command to run. And if you put a command to run, instead of giving you a shell session on the remote machine, it will log into the shell, tell the shell this command to run, communicate the output back to the standard output on your local machine, and then quit. And so actually what I'm going to get is the output of qhost on my local machine, as if I was like catting a file or something on my local machine. That's pretty cool because then I could pipe that into pipelines on my own machine. Or if I could have like an R, I can read from a pipeline. And so I can actually basically directly import that live. Where's my R Studio here? Say, I could use bare R Studio here. It does, this is not really important for you to follow along just because we only care about the output of this. But basically, I'm going to run this little blob of R code here. And the first way it starts off is a read.table with a pipe coming from SSH. And so we're going to directly suck in the qhost output, a live qhost output directly into R there. So maybe I have the copy and paste stuff on the on this file. What slide are we on now? This is 17. So it's a little lower. Here's the blob of R code. Okay, so we'll go to like here. Well, maybe I'll do it a little bit slower than that so you can see what comes out of the read.table. Okay, so that's the read.table from a pipe. Did I hit return? Are you running or? There we go. And if I look at the variable n in R, that is a data frame with the columns and rows being parsed out of the qhost output. So now it's just a matter of sort of formatting that into a nicer form because some of these numbers have G's. They have the metric suffixes on them, the Gibby bytes and the Mebby bytes and stuff like that. We got to get rid of those. So the next blob of our code just rewrites the columns that are problematic right now. So like here we basically just we apply a function to sort of decode those suffixes, turn them all into Gibby bytes. and then rearrange the table because there's a bunch of columns we don't need. So we run that, and now if we look at n, it's sort of been cleaned up a little better. And now you see the node names is the host name is the row name. We've got the memory in GB bytes here, a column. We got the number of CPU cores here as a true number of CPU cores as this column. And then we've done the division, memory divide by core, because this is sort of a key number to target. Gigabytes of RAM per core. So we've got those columns here. How many rows is that? Oh, it was, oh, it, okay, what is the, isn't, oh, is it just n row? Yeah, 802 rows. There's roughly 800 nodes in Hoffman. Let's look at the distribution. I think one of those nodes is currently out for maintenance. So there's a row with missing numbers there. That's a node that's kind of probably got hardware trouble and has been rotated, is sort of dead right now. We're going to adjust our table by removing that row because those NAs are annoying to deal with. And so then we can start doing histograms and stuff on those columns. So give me a table of the number of cores per node column. So this says there is, say, 378 nodes with 36 cores. There are 138 nodes with 24 cores. There are 97 nodes with 48 cores. So ignore the ones that are very rare, right? In terms of deciding kind of what you're going to deal with, forget they're shaded in gray here. The bright white ones are the most common cases. And then we could also do a little histogram there to see it visually if we want. So there we go. So basically that is the distribution of number of cores per node on Hoffman. And that already tells you a bunch of stuff. For example, 4 cores, which is a quarter of 16, that's already 20% of nodes are kind of down there below, if I kind of do the 16 and lower, well, this is only one guy has got 4 or something. That's you can just ignore him. But 161 of 800 nodes have only 16 cores. That means if you're looking at, say, 4 cores, for 20% of nodes, 4 cores is already a quarter of the node. So if you're, the scheduler is trying to fit all these jobs into all this 800 nodes and stuff. So a lot of the times it's got fractional nodes ready and stuff because somebody's running a job and, the nodes isn't full yet, but it's not, their job isn't using the full node yet. So you're kind of, the typical state of a node at any one moment is fractional, right? So if your jobs are requesting a number of cores such that only entire nodes qualify, well, then the scheduler has to work hard, right? If you ask for 36 cores, first of all, there's over 300 nodes where that's not even possible, right? They just don't have that many. Second of all, if you ask for 36 cores and the machine has 36 cores, which is like half of them, it has to completely empty that machine, right? It has to get everybody off that machine to be able to give you all 36 cores on that. So this is why it's important to understand the distributions of these things, because once you start making resource requirements that are large fractions of nodes, you start to really change the picture of what fraction of Hoffman is eligible and how long you're going to wait for it. Let's look at the memory, say. I think the raw numbers have this where's the RStudio? So the raw numbers kind of, there's like some 62.8, 62.9, and so on. That's sort of annoying. Let's round to maybe units of 8 because that'll kind of collapse those together. And so here it is on the slide with the uncommon ones grayed out. Although you may be interested to know that the largest node on Hoffman has 6 terabytes of RAM, right? So that's grayed out because that's only one node, but there is a 6T RAM node in there somewhere. But the common case is down here, 64 gig RAM, 200 nodes. There's a quarter of the cluster is already, 64 gig of RAM. So a quarter, if we're talking about a quarter of a node as something you want to target, that means a quarter of the cluster, a quarter node is only 16 gig of RAM. Okay. Here's the distribution there. And the other number that's very important to keep track of then is the kind of RAM per core average. Because if you sort of, you're usually not thinking about the node as a whole, you're more thinking about sort of like, oh, I need this many cores and this much RAM. And in that case, sort of like you want to keep track of RAM per core on average, right? That makes more sense than just absolute number of RAM on the node. And so that's an important number to track. Maybe we'll track that to tenths of a 0.1 accuracy. So there's the distribution for that. And so what does that look like? Well, where's the common range? Well, first of all, 470 nodes, that's 5.2. So for about half the cluster, there's about 5 gig of RAM per core. And so that helps you kind of also size your jobs, right? So if you need to do something with 15 gig of RAM, well, that's on a typical node, that's kind of like 3 cores worth of RAM, say. So it doesn't really make sense to say ask for 15 cores and like, oh, I'll only ask for 1 core because maybe that'll be easier, but I need my 15 gig of RAM. So I'll say 15 gig of RAM, 1 core, thinking that, maybe the lower cores is better for the scheduler than the RAM or something. No, the scheduler is basically in a situation where by the time 15 gig RAM comes around, it's sort of like 3 cores worth of RAM anyway. So it doesn't make sense if your problem can use 3 cores to just dial it down to 1. They go together, so they scale together.
How do you actually determine the
Yeah,
amount of RAM
yeah, that's
I'm asking direct to the RAM, right?
oh yeah, that's a big part of this task. And like, I don't remember if it's today we get to it, but we will talk about that problem multiple times over the 3 days, and that's a big part of it, just how you figure out, or to the extent that you can control, how do you control the size of RAM your jobs need? How do you figure out what they need or how much flexibility you have, and how do you choose the right number? We've got to talk about that. Yeah, that's a big part of it. But the first thing we need to understand is what the targets are. And so this page is showing you kind of what the targets are going to be like. Because obviously, to have a large number of jobs run at the same time and to have not wait very long for the jobs to start, you've got to size things to these distributions, right? These distributions are sort of telling you, like, if you want to target a large fraction of the cluster, these are where the numbers are at. Okay. Okay, all of our copies are done. They've been done a little while. The discussion there on resources took a little while. And actually, maybe it's 2:30. So that's been an hour. Maybe we'll take a 5-minute break here. The bathrooms, if you don't know, are on the whiteboard here in the corner. We are good here. We basically have completed this slide, and we will start with our case study and looking at the files that the copy pulled over. That's where we pick up after the break. Okay, so we'll take a 5-minute break, 2:35. We'll pick up again. What are people using? Windows?
Yeah.
Do you have any Linuxy stuff on there?
You mean
Like
like,
Cygwin,
I have mobile extension.
mobile external for your access to Huffman, but do you have anything locally installed?
No.
So you could consider installing Cygwin, because that will actually give you a Linux-like environment on your local machine. And you can run kind of Unix pipelines and all the stuff and so on your own machine. I mean, obviously you can do that in Huffman too, but sort of like, it's nice to be able to sort of do things locally too as well.
Is it more like VM?
So Cygwin actually is a different strategy. Cygwin is essentially it's a giant DLL that makes the user side, that presents the user side of Linux and internally translates them to all the Windows system calls. So you can take software that's written for Unix, compile it. It has to be compiled, but Cygwin has a huge distribution of precompiled stuff and an installer that just what things you want. It just pulls them from repositories. You don't have to compile it yourself. But it's all this Unix software that's been recompiled against the Cygwin DLL. And so the software thinks it's talking to a Unix operating system, but Cygwin is translating it all into Windows system calls. And so it's not a virtual machine. It's more like an emulator. Not, it's sort of like an adapter layer. It just sort of does translation. So that's one option. There's Microsoft's official solution, which is the Windows subsystem for Linux, which is a core part of Windows. It's an optional component, so you have to click the right place to say, I want that installed. And at that way, you can download real Linux distributions like Ubuntu Linux or whatever. And then it runs them in sort of a lightweight virtual machine. And you get a window where you can interact with what looks like a Hoffman or whatever on your local machine. It's basically a virtual machine. Yeah, that's a virtual machine running a virtual machine. there are other things you can do. You can use, virtual box. You can get other virtual machine software too if you don't like Microsoft. The Windows subsystem for Linux is sort of the officially supported solution these days. But and you're on Mac?
Yeah, the M4, the newest Mac, the most recent.
So you're on M4?
M4, yeah.
How much RAM you got?
224, just the best for the Mac Air. So I choose Mac Air, not the Mac Pro.
So Apple Silicon is kind of nice right now because they have the unified memory where all memory counts as GPU memory.
Yeah.
And that means you can run AI models on that thing pretty well. So actually mine is a little older, an M2 Max, but I got 96 gig of RAM on this laptop. And that means I can run fairly large AI models totally locally because it's like I have 80 gigabytes of graphics RAM. And even a high-end gaming laptop is like 24 gig of graphics RAM. You need multiple GPUs to get up to 80s, or you need to buy like the crazy NVIDIA GPUs that are like 10K, $10,000.
Yeah, so you have 90 RAM, right?
96.
96, oh crazy.
Yeah.
So
And they do go up to 128, but this was not a cheap laptop.
what's the brand?
And this is the Apple. This is the M2 Max.
M2 Max.
Yeah.
Oh, M2 Max.
So I think actually the M4 Max, you can actually go all the way up to 128 gig of RAM, but you don't like the price.
Actually, exactly.
Yeah. And actually I only got the 2 terabyte solid state disk. Oh God, I feel sad that I didn't spend even another $1,000 and get like a 4 or something, because it's like the 2 TB disk is like so limiting once you start doing AI models, because each model is like 100 gig or whatever, and it just you want to play with them, so you got like 5 or 10 of them or whatever, and then oh gosh, the space disappears.
I think it's much more useful, especially AI has its benchmark, bench, and other L bench, so we can deploy it locally.
So actually, like my favorite local interface right now is LM Studio, and you see what I've got loaded up there is Qwen 3, Alibaba. Yeah, Qwen 3.
Oh, Qwen 3.
30 billion A3B. This is the mixture of experts version. This is like a 30 gig RAM. So right now it's about 30 gig of VRAM being used for this model. It's been running the whole time. Here, I just leave it open these days. And then we can give it something to do, like have we run anything interesting lately? Yeah, we could ask it to explain this R code. Let's see if it can do that. Okay, let's give it this R code. Here, from here to here, that's all our R code. Let me take out the comment here or whatever. Okay, so we're just going to give it this blob and say, explain R code. And you actually see the token generation speed is pretty fast.
Yeah, and it's helpful for the sensitive data and flavors.
Yeah. So this is running completely locally in this machine. No network interaction right now. This data isn't leaving. Glenn loves to think. Eventually he will finish his thoughts and then he'll write his answer.
Yeah. I hope I can buy one, or someone, or the company can buy one.
But you can, there are people like most of the models come in a whole range of sizes down to like 4 gig, and even 4 gig, they're just not as good. But
yeah.
But you are an Apple Silicon, and you can, grab LM Studio and start running smaller models and stuff.
I would do that.
Yeah, I would recommend playing around with it. Oh, hey, finished. Let's see if we can make the window a little. The provided R code retrieves and analyzes system resource data from a high-performance computing cluster Hoffman 2. This retrieves the data, mechanism SSH to connect, execute qhost command, filter out these lines, reads the output into a data frame N, unit conversion function, purpose, convert memory values in units, KMGT, 2 gig, gigabytes. I mean, it's doing pretty well. Clean the data set, missing data handling, data analysis. You know, anyway.
Question related to that, like I was trying to run Studio in through Hoffman because my local system doesn't have that much memory. And so I don't know how to assign the memory for the R, because I guess R typically use a certain amount of memory.
Will it be dynamic? But I mean, you've already seen that the RAM per core is like 3, 4, 5. You could do the R session, I suppose, with 1 core, but like, I don't know how much data you want to import into your R session or whatever, but like, I mean, it wouldn't be unreasonable to say 3 cores, 5 gig of RAM per core, 15 gig of RAM total, right? But I wouldn't go super tiny, right? I wouldn't go to like one core, 3 gig of RAM or something. That's just too small. I mean,
I was trying around like 14 cores and 20 gigs per core.
20 gigs per core is too big.
Too big, okay.
Right. So you should dial that down and increase the number of cores. You can ask for the product to still be big, but you should balance the two numbers better.
So I was asking how to manage that.
Yeah. So what was it? 3 times 20? What was your two numbers?
So 14, that was 20.
14 times 20?
Yeah.
Well, that's too big, right?
That's too big, yeah.
Because 14 times 20 is 280
Yeah.
total. And 280 total only qualifies you for 376 and 504. And first of all, that's only 90 nodes. Like a 10% of the cluster could qualify. And those nodes will have to be fairly empty to be able to satisfy that. You have to wait a long time. Yeah. Was that what your experience with? They just wouldn't start?
Sorry?
Was that your experience? They just were hard to start? You would wait a long time for them to start? Yeah.
I mean, sometimes it works, especially during weekends. I guess it's pretty fast, like within 5 to 10 minutes. But weekdays are pretty difficult. Sometimes it takes an hour, sometimes it doesn't qualify. So
Well, we've got 2 people still at the bathroom or something. Their laptops are here, so they're not gone, but they're taking a while, so we'll wait, I guess. Another important question. Yes, so when we, probably day 2, we'll have good examples of what happens when you cut it too close. Yeah. The answer is you should be more generous than not. Yeah. I don't know if you caught Quen's final output, but Quen did a pretty good job there. He basically correctly determined the purpose of this R code and decomposed its pieces into how they work. And yeah, did a very good job. For locally running, Quen 330B is, I think, the sweet spot right now. This model just came out.
This is the proven. And someone said the cloud is also proven.
Yeah, I think Quen is a strong model. You know, I think OpenAI just kicked one out and like it only was the leader for like 3 days before Quen just knocked it out again. So it's like models only last like a week now. It's like there's always this fight now. The other one I like for local right now is the Google Gemma 3. And that's nice because Gemma 3 is a vision model. So you can actually feed it images as part of the data. It's multimodal, whereas Quen 3 is text only. Although Quen 3 is also a tool user. So Quen 3 knows how to talk to external tools. Gemma doesn't, but anyway, it's a whole universe. We should probably have another workshop on these things now. All right, well, the other guy hasn't come back yet, but it's been 50, closer to 15. Well, we're getting close to 15 minutes here, so let's continue. So the case study, as I said, is going to be a whole genome bisulfite. The bisulfite alignment stage. Obviously, this is not a bisulfite workshop. We're not going to worry about the stuff that came ahead, like quality control or kind of getting the reads sort of ready for this business and what happens after the alignment. But the alignment is sort of a large problem that is a good that will have all the components about this how you work with Hoffman this way. And so we will use this as the example. So it is this is the Nature paper it comes from. It's a 2013 Nature paper. It's a while ago now. But the reads are 101 nucleotides, human whole genome bisulfite reads from there as part of the Nature publication. They're deposited into NCBI, so you can get them out of the short read archive SRA. These are the two SRA accessions here, and remember everything underlined is a web link. So I kept two samples. I mean, you're doing one sample is sort of like not enough to show everything that goes on because if you can do two samples, you could do 20, but 1 to 2 is sort of a transition. So we'll do two samples. And the first sample has about 450 million reads, and the second sample has about 350 million reads. These are H1 embryonic stem cells that have been differentiated to different tissues. In these two samples, I think it's mesendoderm. These are two bioreplicates of this tissue. So yeah, so the main part, the slow part of a whole genome bisulfite analysis, the primary analysis of bisulfite data is the bisulfite alignment stage to a reference genome, here the human reference genome. And as I said, whole genome bisulfite projects tend to be large number of reads per sample. Then you may have quite a few samples, and bisulfite alignment is slow, and you put all that together, and that's what makes this kind of be a big job. So, okay, so as we've been talking about, the way to approach this is to shard those FASTQ, the reads will be in FASTQ files, GZIP FASTQ files. We want to shard those into many small pieces so that the entire input data has been partitioned across many pieces. And then we will align each piece as a separate job on Hoffman so that they have a good chance to run many of them at the same time. And they're all going to be small, so they're not waiting a long time to run either. And then at the end, we'll have to put the results back together again. So after the alignment, there will be BAM files. We'll have all these one BAM file per part, and then we got to make one, we want at the end one BAM file per sample. And so we'll have to undo the splitting that happened at the beginning. Okay. And yeah, so we already talked about how this is sort of like a lot of bioinformatics problems are like this. They're sort of embarrassingly parallel, as it's called. And for a lot of them, the right solution to kind of fit them to Hoffman is shard into tiny pieces. Okay, so let's start looking at what came down in this giant copy that we had here. So you should be in your own Scratch directory in the W1c directory. And now if you look in there, you should have files, right? So just check. Oh, I see what happened. I did my copy into the directory that I did the slide prep on. So that's why I already have all the finished products here. So that's a little unfortunate. I wish I realized that sooner. Let me, I have to do another copy, but we'll be able to continue before that finishes. Okay. So I need to make a fresh copy because my W1c already had all the products in it. Okay, so I will get another session going where and then where's the oh, we don't need, whoops. Are we, oh, is that the cable? What is that? That is really, really strange. What's happening is my laptop screen is going pink. I guess it's not showing it. Everything looks okay on there. That is not, I don't know if you can see, but there's like my screen is turning all pink. like, this is really strange. I'm going to close the Quen here. If, there we go. Goodbye. So does that help? No, that doesn't help. That's really scary, laptop. Okay, well, maybe I have to look at that screen and just ignore this. Okay. That's not, it's like my neck is gonna break if I try to do that for 2 hours. So can I flip this around? How are we doing with Zoom? Is Zoom video still stable?
Yes, I can still see your screen.
Great. Problem is I can't see my own screen. Okay. So, all right, I'm now facing the projector. Or, oh, now you decide that everything's fine. Yeah, whatever. What? Whatever. Okay. I do think this cable is sort of related to it. There's like this video cable is bad. Oh, I'm not gonna play with it. All right, so we're gonna do it this way then. Okay. All right. So projector's okay, laptop screen's okay, and Zoom is okay.
Yes.
Okay. Hopefully this is stable now. Okay. Um. There we go. Well, that's interesting. It's when I switch to text edit that I get my purple screen. Very, very, very strange. Okay. If I quit text edit. And reopen text edit. Weird. Very, very strange. That's that's like some kind of OS bug or something. That's not text edit. Text edit can't do that. But we're even text edit stable again now. Okay, so okay. It looks like whatever that is done, but that was very, very strange. Okay. Okay. So this is what you should be looking at. This doesn't have everything done yet. This is the as distributed version. Okay, so the big files are here. So, I almost always use ls-la. That shows you everything all the time. And here you see the column of byte sizes, right? So this is clearly a large file. This is clearly a large file, right? How many commas are in there, right? So, right, that is a 41.5 gigabyte file. And the other one's 32.5 gigabytes. And those two together are already 73 gigabytes. And that's why the copy took a while. Actually, I think there's some more gigabytes in here. So if we ask, there's another 18 gig down in there. So we're probably pushing 100 now. Well, it's 87 or something, whatever. So anyway, that's why the copy took a while. Let's look at these. We've got two FASTA files. These are the reads for the two samples. Okay, so we could do less. And less is smart. Less knows how to understand gzip text files. So this is a gzip plain text file. Less knows how to deal with those. So here we see the contents of it. And maybe you've seen hopefully you've probably seen FASTQ files before, right? FASTQ is a 4-line per read format. That's read number 1. That's read number 2. That's read number 3. Reads start with an @ sign and then some kind of naming, right? This is sort of name information. Then you have the ACGTN sequence. Then you have a plus sign. And because this file originates from NCBI SRA, they've actually repeated the naming. That is an optional thing in the SRA form, in the FASTQ format. Most people don't do that because it just makes the file bigger, but whatever, NCBI. It's not illegal, but it's just like waste space. And I mean, there's just no point. In fact, this third line is sort of like no point at all. I don't know why FASTQ put this stupid third line here. It's kind of pointless. then this is the per base quality scores, which is an indication from the sequencing instrument as to the instrument's confidence that it has made the correct decision about whether the letter is A, C, G, or T. And we don't really care how those are encoded. It's just that this is the format of the data. All right, and then this is just a text file with a lot of lines, right? Because I said like 500 million reads or something. So that would be 2 billion lines or something when uncompressed. Okay, so another way to do that, which, depending on how many, I don't know what you've seen. If you're coming from Workshop 1B, you would have seen this stuff. But if you're coming from outside, maybe you haven't seen gzip used this way or not, or so on. But a common way of using gzip files in pipelines is to use gzip to make a temporary uncompressed stream. So this gzip will either compress or decompress depending on what options you give it. The -d means decompress, and then I'm giving it a gzip file, so that matches with the -d. But the -c is the interesting part, and that means gzip turns into a standard input to standard output filter. And so we're reading the file from disk, but the -c means that we do not uncompress the file on disk or modify this gzip file on disk. Instead, we produce to standard output of gzip the uncompressed copy as a copy. So this is a great way to adapt any plain text using tools and stuff to compressed input in this case. Here, we're going to leave the file on disk. We just uncompress it on the fly and feed it in whatever. The way that the shell pipes works, the way the operating system and the shell cooperate to make these pipes work, is that gzip will run a little bit ahead of less, but if less doesn't ask for the entire file, gzip will not generate the entire file. This little pipe acts as a little buffer in memory, and there's only a certain amount of stuff, a pretty small amount of stuff can fit in that buffer. And so there will be a fairly tight coupling of as fast as less eats the input, gzip will be generating the output. But if less dies early and doesn't use all the input, gzip will be killed too and not generate all the output. And the execution time will be coordinated between these two to sort of keep them in sync and so on. So this is a great way to do it. I don't have to unzip the file, make a copy on disk and so on. This is all sort of on the fly and only as much as needed. So if I pipe that to less, I see something which is basically looks like the way when I just less the gz file directly, and basically this is what less is doing internally when you ask it to view a gzip file. And I can look at, say, the headed file. You notice that I got that output instantly. And if I type Q to quit less, I also get my prompt back instantly. That gunzip did not have to get anything like to the end of the file, because that would take minutes and minutes, because you saw how long it took just to copy the file to so on and read it. And gzip would have to read the whole 40 gigabytes or whatever it is, and so on. That wouldn't be instant. And so that demonstrates we'll be using gzip like this in tons and tons of pipelines throughout the things, but I just wanted to show it in a very simple way first before we use it in fancier ways. So let's start transforming this file in various ways. Okay, so we can take this sort of this thing here, which sort of spits out a uncompressed copy of the file. And a cool thing to do is this little trick with paste, where paste takes multiple command line arguments, and the dash means standard input. And now you see I've said standard input 4 times. Paste is a tool that reads multiple lines and reorganizes them to multiple tab separated columns. And by telling paste that there are 4 input files, but they all should read from standard input, what it means is we take the 4-line format that basically the incoming FASTQ is, and we rearrange it into a 4-column tab separated file where now there's only 1 line per read, which is much more convenient because now reads are lines, and lines are what all the plain text stuff likes to deal with. So I will then pipe the output to less so that we can see what's going on in this transformation. And so now it's a little hard to read because the lines are so long. I mean, maybe if I really shrink down the font size to something ridiculous and make the window wide, maybe it'll just so that you believe that it's sort of like what happened to, can I make the, there we go. Anyway, there you see the sort of column 1, column 2, column 3, column 4, but you can't read it at that size. So let's go back bigger. So that is 1 line of the new output. That is 1 line of the new output. And between here are tabs. But we basically reorganized the file from 4 lines per read to 1 line per read, which is much more convenient for manipulations. Then we could do stuff like, suppose we wanted to pull out just the sequence. We could pull out column 2. We could cut field 2, cut by defaults to tab separated stuff. So there we go. Now we've got 1 line per read, naked sequence only. All right. That could already be useful depending on what you're doing, right? So
Dash should be equivalent to number of rows, not number of rows, but it's basically converting each read into 4 columns.
That's this part. Then this part is throwing away all columns except column 2. Column 2 is what used to be second line of 4 in every group of 4. If I instead use cut -c 2 to the end, what that means is throw away the first character. The first character is that @ sign at the start of the read names, right? So like here, like you see this, the read names start with this @ sign. Maybe I don't want that because then we're going to do something with it. So if I do that cut -c 2, you see I got rid of the first character, which is an @ sign. Now, awk is one of the tools maybe you saw in an earlier workshop, or maybe you've experimented with yourself or run into. Awk is a text transforming tool that kind of works line by line and takes a little, its command line arguments essentially specify a mini program for what you want it to do to each line. And so awk is very useful for sort of doing simple transformations that aren't too complicated, and eventually your transformations get complicated, you have to use Python or something. But for like little command line stuff that's sort of one-off and easy things, awk is a great tool. And now we're not going to get into awk. If you know some awk, that's great. If you want to learn awk, that's great. I give you a web link here to like an awk stuff. Google will tell it to. Any of the AIs will be happy to write awk for you if you tell them what you want to do. But basically, the command line options here to awk are saying your fields are separated by tabs. And then this is what I want you to do on every line. On every line, I want you to take the first column and put it in the awk variable name and split name into parts based on spaces. So for example, if you look at the file here, you see that the names are actually have components, right? So this is like word 1 of the name, and this is like word 2 of the name. And so this breaks out the column 1 into space separated chunks. And then this printf means produce output. This is the format that we want the output to produce, and this is where the variable parts of the output are coming from. So I want you to produce basically what looks like another FASTQ file. So each read starts with an @ sign and then a string. The first string I want you to pull from is the second name component that we just split up. Then I want you to put the first name component. So basically what I'm doing is I'm reversing the order of those 2 name components. And then a new line. And then we know that the second line of FASTQ should be the sequence. Well, that's in column 2 right now, so that goes there. And then maybe we don't want that stupid repeated name in the third line. So we just want a naked plus sign with no stuff there. And then maybe we want the per base quality scores here in the 4th line, and that comes from the 4th column right now. And so basically, if we run that kind of thing right now, we will see that we've done a FASTQ to FASTQ transformation where we have swapped the order of the name components, gotten rid of the stupid repetition of the name and so on. And we sort of de-SRAified this sort of FASTQ format and made it more looking like a normal FASTQ file that you get from an Illumina sequencer. It'd be very easy to transform this to also do like FASTQ to FASTA conversion. Like suppose we don't want the quality scores. We could do that too, right? So we could replace the @ sign with a greater than sign because that's how FASTA files have the read names. And then we don't have the quality score stuff. Only 2 lines per read in FASTA. And then we don't need the quality score, so that stuff goes there, right? So now I've got a FASTA output from that FASTQ. So this is now a FASTQ to FASTA conversion. So that is just us experimenting. Oftentimes when you're developing pipelines like that, you want to just kind of build them up in pieces, use less to check out your work. We are ready now maybe to do this whole transformation and write it to a new output file. So this part of the code here is just what we had developed. It's this stuff right here. That's the same. What are we changing in this last invocation? Well, I'd like to write the new FASTQ file as a gzip FASTQ file. So I would take the uncompressed output that's coming out of awk, and I want gzip to smush that down into a gzip file. So that means I need to do -c because I want gzip to work as the standard in, standard out filter kind of mode, not reading from disk. So the -c activates that. The double-best is a hint to gzip that I want it to spend a lot of CPU time to try to optimize I want the smallest file, and I want you to work hard to do that. You could also do fast, which says that I want you to not take much time and compress it as much as you can, but try to be fast about it. Don't take a lot of CPU time to do it. Either way, whatever you like to do. And then we finally do a shell redirection and write the output to a new FASTQ file, which I'm calling the dsrafied FASTQ file. So we could kick that off. Okay. Oops. And what you see is, I guess it's working, right? I mean, we haven't got a shell prompt back, but how long is this going to take? We don't really have any idea right now, right? Because nothing we did with the less was very much of a stretch. That wasn't, it's like 1,000 reads we saw at most or something. So the moment we have no idea, like, am I 5 minutes away? Am I 5 hours away? Like, whatever. So, okay, so let's abort this and maybe we can do something a little better. So Control C, that quits that. Okay, so that just stops it wherever it was, kills it. If you look at files, we do have an output file, but it's totally not complete, right? Because look at the file size, right? We expect an output file size comparable to the input file size here, right? Because we didn't do that much transformation. The input files are like this. This is this. There's like 3 digits missing. I mean, this is like way too tiny, right? So actually, we didn't make it very far there. Okay. We could ask how many lines did we get out of it, right? So we could actually ask gzip to uncompress the partial file. Now that partial file is probably broken at the end, and even gzip might know that because compressed files have to have a certain structure. And if you just stop them in the middle or something, it's like obvious to the tool that it's like, this is not a complete file. So gzip's probably going to complain and whatever, but gzip will be able to decompress that file to that point. So we will get output from it. We could pass that to word count, find out how many lines we got out of it. Well, we got about 800 million lines out of it. So we did about 200,000 reads worth in that time. That would be enough for estimate. We know we let it run about a minute or something. So it's 500 million divided by 200,000 multiplied by a minute. That would be our estimate for the runtime for the whole thing, right? That's kind of annoying to do. So one of the things that's cool in pipelines is you can use this tool called Pipe Viewer, PV. PV is not installed in Hoffman by default. So like if you ask for PV or ask the shell, where is PV? It says, I can't find it. I do have a compiled version in my directories. And if you run this little tools here, that will adjust your path to know where PV is in my place. And now if you say PV, well, PV is running, but it's waiting for input. So you don't see anything, but you can say man PV and stuff here. You can say which PV. You'll find out that the shell knows where PV is now. So now we can play with PV. PV basically acts like cat. It does the same thing as cat. If you put files on PV, it just writes them to standard output one after the other. If you put PV in the middle of a pipeline, it'll read from the standard input and write the same thing to the standard output. Why bother? Well, it has a nice side effect. The side effect is that it makes text mode progress bars as things flow out of it or through it. So all I'm going to do is take the command that we just interrupted that was running for a long time. Gzip takes its input from this guy. So instead, what I say is PV starts spitting out this file. But because PV opens the file and stuff, PV knows how big it is and it knows how much it's already spit out, and it will be able to make very nice progress bars based on that information. So then we pipe the output of PV, which is just the gzip file, through gzip decompressor. Now we got a plain text version coming out of that. Then we go through the rest of our pipeline to transform it how we like. Then we are piping to gzip again to compress it back down, and then we're writing our output file again. So all I've done is I've just adjusted the input side of this pipeline a little bit. And now if I run that command, you will see a very cool progress bar. So that's coming from PV. So PV is telling you, oh, I've spit out 5 megabytes of compressed gzip files. So PV doesn't know what file it's got or whatever. It doesn't care. It's just counting bytes. So it says, oh, I've pumped 9 megs out now. I pumped 10 megs out now. I've been running for 20 seconds. I am spitting data out right now. The other side of the pipeline, whoever that is, it happens to be gzip-c-d, is eating my data at 600 kilobytes a second. This is actually like a little text mode progress bar that'll actually grow left to right as it finishes. It's just that progress is slow here. We haven't even reached 1% yet. And it's saying you are 0% of the way through your file. And the estimated time of arrival for finish is 18 hours, 35 minutes. So that's a long time, but at least we know what it is. So we could leave this running, open up another shell session, continue work elsewhere. Of course, at 18 hours, this is now big enough that already this is something we kind of want to split into pieces and run in jobs on Hopin, but we don't have that infrastructure yet. But PV is a cool little tool that you should know about if you didn't know about it. So this is, I'm not going to wait 18 hours, so I am going to hit Control C and abort that pipeline, and we now have another partial file. We were just overwriting the old copy of this thing, so we have another partial file here. Whatever, we should probably clean that up because we're going to abandon that one. But let's see where I've lost where we are. Slides here. Okay, so here. But here's another cool thing I want to get into now. Before we start doing Hoffman jobs, I will show you how to do multiple jobs running on one node. And because everything that we do is all Unix stuff and whatever, if you're on Mac or you're on Linux or you're on Windows with the right environment like Cygwin or WSL, everything we do on the Hoffman node, you can also do on your local machine. So you can also do this backgrounding stuff we're about to do now on your local machine and so on. So I'm going to take the same pipeline we just ran. I just hit up arrow to pull back my command. That's exactly the command we just ran. Actually, I'm going to go back to the pre-pipe viewer version because when we're backgrounding, we don't really want the progress bar because that's going to interfere with what we're going to do after. So I'm going to go up arrow to the point where the one before we did PV. PV is more for interactive sessions. Okay, so this is the last command we ran that is the same thing as the version with PV, just doesn't have the PV in. And all I'm going to do is add a single character to the end. I'm going to add an ampersand. Okay, that's the only thing I did. And now I hit enter. And now you see very different. I immediately got a shell prompt back. You also see the shell. It turns out the shell printed this. The shell tells me it told me something. What does that mean? Well, I'm going to give the shell command jobs. Here, jobs do not refer to Hoffman queue system jobs. These are Unix job control jobs, shell jobs. These are jobs running just in your shell kind of environment on one node. The brackets means that this is shell job number 1 in this shell. Okay. Jobs is giving you the list of all the jobs that the shell is currently aware of. This is job number 1. This is the state of the job. Jobs can be running or they can be stopped. Okay, so this job is actually running. We just have to trust it right now. We will look around in a second to verify that's actually happening. This is a reminder of what the command was that's running. Let's see if we can convince ourselves that that thing is somehow still working even though we've got our shell prompt back. So I'm going to look at the file listing again. That's a lot of irrelevant files. Let me just look at the file listing for the relevant file. Okay, so that's just ls, just for the one file. Okay, and I'm going to hit up arrow a couple times and run that. Okay, and what do you notice? What do you notice? File size is growing. Yeah, it looks like it's actually progressing, right? What are other ways we can kind of see what's going on in our node? So this PS command, which takes a lot of arguments and so on, but maybe this one is kind of a good default for us. This shows us all the Unix processes, as they're called, that are running on this node 7361 that we're on right now. And what do you see? So you see these things called process IDs. That's a unique identifier that the operating system refers to the process by. What users running them, I asked for PS only to show myself. User is a shell variable. That's another one of these shell variables that's sort of set at the beginning of every shell session. So that is just your own username. Okay. Size and RSS are related to how much RAM the thing is using, but let's not worry about that right now. S time is the start time. This is a 24-hour clock. So some of these, like the SSHD was started at 2:49 p.m. The gzip was started at 15:08. That's 3:08 p.m., which is like 3 minutes ago, which is right. Okay. TTY, don't worry about. Time is how much CPU time that it's been using, the total amount of accumulated CPU time it's been using. You can see that right now, actually, our pipeline is dominated by the final compression. This is the slow part of our pipeline because these are the other pieces of the pipeline, the gzip decompressor, the paste, the cutter, the awk transformer. This is the gzip recompressor. The gzip recompressor is cranking up all the CPU time. The other numbers aren't very big. This tells me that the slow guy in the pipeline is the final compression. Probably if I did gzip dash fast, it would be a better story. Or I'll show you at some point, like Facebook has Z standard, which is basically a drop-in replacement for gzip, and that compresses a lot faster than gzip. Gzip's just been around for decades, and every platform basically has very good support for gzip. Z standards is kind of new, but one of the weaknesses of gzip these days is that its compression is kind of slow. Okay, and then, so what are the other things? So obviously this is stuff related to the pipeline. Each of those is one process because each of those is one program, okay, separate program running. This is my shell. This is the shell I'm talking to right now. This is when QRSH opened up the session onto this node, it had an SSH into this node. This is the SSH daemon that's the corresponding half. So QRSH started this SSHD, this SSHD started bash, and then I started via this bash the rest of this stuff, right? So this is all my pipeline that's running in the background. This is actually the PS command itself. So I asked PS to show all processes. PS is itself a process. It's showing itself in this list or whatever. So that's one way to see a snapshot of what's going on in the node. Another way is to use, if you just do PS with no arguments, I think actually does default to yourself. But if you, well, if you do this, PS will show you everything on the node if you want. And you see there's a lot more processes than just mine on the node right now. You can also do top. That's kind of a cool display. That shows you, and it's updating, it looks like every 2 seconds maybe. You see the timestamp here. Maybe it's every 3 seconds. Yeah, it looks like about every 3 seconds is the update rate here. But it shows you the processes. It can sort, but I mean, if you do question mark for help, you can see all kinds of stuff you can do in top. By the default sort is, I think, by CPU time. So this gzip is using 100% of CPU. That is the final compressor. That's the bottleneck right now. So he's using a full core. The other guys aren't using, are using fractional cores like 5% because everything's bottlenecked at that point by that final compressor. So the other guys aren't using much CPU because they can produce data so much faster than that final compressor can eat it, that it's all just dominated by single core performance of that final compressor. And then you see other stuff run. It looks like on this node, I'm by myself right now. I see an R session there. So this is some other user of Hoffman right here running an R session. So he's got, and you saw there, he was using 5 gig of RAM in that R session or something, but he's not using much CPU. He's probably just idle in that R session. But anyway, you're on all probably different nodes, so you'll see different stuff. Q is how you get out of top. So just type the Q key. Another way to kind of poke around what's going on is LSOF, which shows list open files, what LS stands for. And here I'll ask it, show me all my processes that are running, show me what files they're touching. So you'll see here that there's a lot of stuff here maybe you didn't expect, but like if we find in here, somewhere in here will be the gzip files, right? Oh, so here is the gzip that's reading the source file and decompressing it. Here, somewhere down here will be the gzip that's writing the output file. Yeah, this is the gzip that's writing the output file. Now, one of the columns here is actually the current file pointer in that file. So this is another way to find out kind of where they are. Like here is the input file, and this number is actually did I do the dash O? No, I didn't do the dash O. So the next line with the dash O 0 will, and then I'll plate that to grep to only pull out the gzips so that you don't see all those other lines. This is now showing you the offset in the file where the program is currently reading from. So for example, we know the file size of this input file. That's this number. Well, this is actually the point where the decompressing gzip is reading from right now. So we could actually compute kind of the progress directly from this information, right? So we could say it's at this byte of this total number of bytes. And so it is at 0.6% through the file, right? So we can kind of use tools to kind of poke at the processes and find out where, oh, you're reading from this gzip file, where exactly are you at right now? So this is ways you can sort of like find out where things are, that things that don't get progress information, you can sort of get progress information out of them. Watch is a program that just runs a shell command over and over again. So basically, I just took the last LSOF grep pipeline, wrapped it in single quotes here to protect that from all the shell coding. So watch gets the pipeline correctly, and watch is just running that every 2 seconds right now. And so you will see these file pointers here and here. This is the input side, that's the output side. You see them going up. We're monitoring the progress here. Control C to get out of watch. Okay, so jobs again. You may have more than one job running. We'll do that in a second. But what if you want to bring a job from the background back to the foreground, right? Suppose I want to pretend like I never did the ampersand or something. So you do that with FG. So I can say bring to the foreground job 1. And now you see I get no shell prompt again. This program pipeline does not produce any output to the terminal, right? It's writing everything to that file and so on. But this job is now back in what's called the foreground. It is as if you had run it without the ampersand now, okay? You may decide after you start a command without the ampersand that you actually wish you had started it with an ampersand. How do you deal with that? That is Control Z, okay? So if I hit Control Z, that you see it interrupted, and the shell kind of showed you the change to the job table. If I say jobs, you'll see the same thing, but the shell knows you're probably interested in that information already, so it just printed it by default after Control Z. So what we have now is that job is still job number 1, but you see its state is now stopped. Okay, and now if you look at with like top or something, you will no longer see any parts of that pipeline at the top of this again. Okay, because it's not using CPU. If we look at the files, like here's the output file here again. Okay, if I just ls that guy, it's not growing anymore. The job isn't killed. Those processes are still alive. They're still using all the memory they were using, but the operating system is no longer giving them any time. We've just frozen it all in place. Okay, that's what stopped means. If we want them to continue, like, okay, maybe you stop them because you want to kill them or something. Well, we'll do that in a second, but what if I want to restart, let them keep going again? Okay, so that you can put them back in the background. So BG background job number 1. And now you see job is running again. That's not like, it's not like restarted from beginning. It's just picking up. We never killed it. We just paused it and now we unpaused it. Okay, so now if we look at the ls again, file size is growing again. And it didn't start from 0. All right, it just picked up where it left off. Okay. Now that's all well and good. But this is an 18-hour job and we're not going to wait for it to finish because we got other things that we want to do. So how do you kill jobs? If you decide you want to abandon them, how do you kill them? Well, you could foreground it and then Control C it. That would be one way. I will put it back in the background. Okay, it's back to running again in the background. Or you could just directly kill it. So you can say kill and then give a job ID. And this says kill job 1. And it looks like nothing happened. And the reason is the timing's a little tricky here. The kill takes a little bit of time, like milliseconds to happen. The shell actually got back to me with a shell prompt before the job finished dying. So that's why I haven't gotten a notice from the shell yet that the job died. But if I do any other command, or even if I just hit enter to get another shell prompt, you'll see that then the shell will notice that this job died and it will inform you. Job 1 terminated. Okay, so this is, yes, yes. So we'll do that in a second. And now you see my jobs table is empty. And if I look at top, it's not there. If I look at the PS, they're not there anymore. The PS is down to just the SSHD from QRSH, the bash shell I'm currently talking to, and the PS itself, and that's it. So all those processes are gone. Okay, the file will now be incomplete or something. There's no auto deletion of anything or whatever, but that's an incomplete file. So that we're going to abandon this computation. So I'm going to delete that output file. Okay. And that file is incomplete, but this file name doesn't make it obvious that it's incomplete. The file size, if you know what it's supposed to be, is kind of a hint that it's incomplete. But one of the refinements that we'll do a little bit later is how do you arrange your file names so that while it's still being worked on, it's sort of obvious in the file name. And then when the job is done, the file name transforms into the final file name. That's a great way to sort of like help you out into realizing what things are sort of done or not. That's a refinement we'll get to later. But yeah, the question is, how do you do multiple jobs? That's exactly the next slide. So we need to have some sort of smaller jobs that we can play with that so we're going to make some toy jobs that just don't really do anything interesting, but just allow us to play with having multiple jobs. So seek is just the stupid little command line program that just spits out the numbers from 1 to whatever. So if you say seek 42, you're going to get the numbers from 1 to 42, one on a line on standard output. So then you could pipe that to stuff, give me the last 3 lines of that, say. So there's the last 3 lines of that or whatever. Okay, so that's just a little program that produces outputs just so we have some output to do something with. Brace expansion, if you haven't seen it before, is a cool feature of the shell. That is a way to produce repetitive things inside the command line. And the shell just sort of like expands it out. It's pretty intuitive once you've seen enough examples. But so for example, this is sort of like X and then curly braces Y. And inside the curly braces, it's kind of like 1 to 10. And you see the shell here expands that into 10 words, each of which is what happens when you kind of follow through the word from the beginning to the end, and where you plug in all the variable, all the number ranges or whatever that you listed inside. What's inside the curly braces could be other strings. So like that'll paste together like that. You can even do crazy stuff where like you can nest it. All kinds of cool things you can do with curly brace expansion. But in this current very simple form, that just gives me numbers 1 to 10. Very similar to what seek 1 to 10 would do. But the difference is that seek 1 to 10 is a program that produces 10 lines of output to standard output, whereas curly brace 1 to 10 is a shell thing that expands into the 1 to 10 inside the command line, and then the shell will reevaluate that command line with that expansion. So it's a different kind of thing. So we're going to do a little for loop to run 10 jobs in the background. Okay, so let's make the 10 jobs we're going to run are to produce 10 files with the numbers from 1 to 1,000,000. Each file has the numbers from 1 to 1,000,000 in a random order. Okay, so I want 10 files. Each file has 1,000,000 lines. Those lines are the numbers 1 to 1,000,000, but they're in each file is in a random order. Okay, that's what I want to be done. Here is we will write it without putting jobs in the background, and then that will be slow. And then we will do it putting the jobs in the background, and then they'll all run in parallel, and that'll be 10 times faster. So, okay, so here's how it's going to go. So let me first kind of simulate what one iteration of that for loop does. So I'm going to set the shell variable lowercase x to 3, which will be like one of the middle iterations of this for loop, just so that I can show you kind of what the inside of this for loop is doing. So the first thing to do is this, and the only purpose of that is to put a leading 0 on there. So it's very nice when you have file names that are numbered, that the numbers contain leading zeros, because let me just do a little Scratch demo here. I already have. If I have a bunch of files that are, that was a stupid way to use the brace expansion because I didn't really have to type them all out. But anyway, you see what happens when you have file names without leading zeros and you sort them. Because the sort is by a string or dictionary order, things like 10 come before 2, because the rule for dictionary order is characters left to right, first difference, lower character at the first difference wins. And so when you compare 10 to 2, the first character that differs is the 1 versus 2, and the 1 wins earlier in the order. So 10 sorts before 2. That's always obnoxious. Whereas if you put the leading zeros on, then they will sort correctly. So this is just sort of the usual thing I do with numbered files. So the purpose of this little lowercase x to capital X transformation, this thing. So remember, lowercase x is just a 3. Capital X is got the 0 on front. What we're doing is we're calling a program printf, which takes a format specification and the variable part, and then the $parens captures the output of that program into a shell variable. So if I run this as a program, you'll see that's what's printed out, the 03. The 2 there is the number of digits. Like if I did %05D, you'll see I get a 5-digit thing on the out and so on. But anyway, the combined effect of that line is just to get a 2-digit 0 padded business, just to make the file names nice. Just sort of a refinement. This is just a progress line. That's going to print something like that. Okay. Here you also see I'm using the shell process substitution, as it's called. Date is a program that prints out stuff like that. We actually call date, capture the output of date, and then substitute that in as a blob of text here. So the echo command sees the output of date there. And then this is the line that's actually going to do the real work. So here, this is shell arithmetic. If you haven't seen that before, $ with double parens is arithmetic. So I can do 13 times 10 plus 4, 134. Here I'm doing X times 1,000 times 1,000. That's a million. Okay. Actually, I lied. I want the ith file to have I million lines. So I want file number 1 to have 1 million lines, file number 2 to have 2 million lines, file number 10 to have 10 million lines. Okay, so that's just X times 1,000 times 1,000. That's a million times X. So the ith file will have I million lines. So that's with seek. Seek then spits out the lines, the numbers in order. Then we pipe it to sort, which one of the options to sort is to do a random sort. And that basically just scrambles the lines in a complete random order. So that basically randomizes the order like we wanted. And then we capture that in a file where the number is the capital X. This is then a hint to sort to tell it how much memory I want sort to use. I want sort to use up to 1 gig of RAM to do its sorting. That'll make the sort faster. We can talk about big sorts later. But but now we should think, is this okay? I'm going to do, if I do one of these at a time, no big deal. I'm just using 1 gig of RAM at a time. If you remember when we started our session today, we did what, 3 cores, 4 gig of RAM per core, 12 gig of RAM total in our session. 1 gig of RAM is no problem. In fact, even if we do 10 of these in parallel, that's 1 times 10 is 10, which is less than 12. So it's all fine. So this is a good number to use, but if we're going to run 10 of them at the same time, much bigger than this wouldn't be great to use. 2 would already be over, given our current limits, say. But anyway, so this is how one part works. So wrapping that in the for loop just means that the insides of the for loop happen with that little X variable set from 1 to 10 in turn. But you'll see that everything in this for loop is completely serial. Every command has to finish before the next command finishes. Every iteration of the loop has to finish before the next iteration of the loop finishes. So here you see it's, okay, the first part, that didn't take too long. Second part's going to take twice as long because we did them, 1 million, 2 million, 3 million. Each one should be a little longer than the previous one. So you see here that they're getting a little slower. Like the first one, only 1 to 2 only took 3 seconds. 2 to 3 took 8 seconds. And now 3 to 4 took 11 seconds, so on. But this is kind of slow. So I'm going to stop it early. If you look in our output, we're actually starting to make the output files. And if I look at some of them, that first one kind of looks like the thing we want. But here's how to do it in parallel. How are we going to do it in parallel? Well, all I'm going to do, I'm going to get rid of the echo. It doesn't make any sense anymore for progress because they're all going to run at the same time. So progress doesn't make any sense. Kill the echo line. I just did a silent decision to put this X line in the same line as the for loop that's allowed. All I did is in the seek line is I put an ampersand at the end of the seek line. So they'll all go in the background. And this for loop will spin very fast and we'll kick off all 10 of them almost instantly. And then all the seek sorts will be running in parallel. So we'll actually have 20 processes running in parallel. We'll have 10 seeks running in parallel, 10 sorts running in parallel. There's a pipeline connecting those two in pairs. But let's see if it works. So okay, so let's run this little 3-liner now. Okay. And then it's time for another break after this slide. Okay. And then we're going to do done here. And as soon as I hit enter, the for loop will go. Okay. So there you see, we just started job 1, job 2, job 3, up to job 10. If I do my jobs table, oh, one of them's already done, right? Because we know the first one only takes like 3 seconds, right? So there you see the shell tells you, oh, job 1 is actually done now. That as soon as it's done, this will be the last time you'll see it in the table. You'll no longer see a table entry for him. I've waited a few seconds. You see there is no longer a number 1 entry, but now 2, 3, and 4 are done. And if I say jobs again, they are out of the table. 5 and 6 are done since the last time you asked. And 7 is done now. 8 is done. 9 and 10 are going. 9 and 10 are still going. 9 is done. Only 10 is left. Now 10 is done. My jobs table is back to empty. So I could have, while those were running, I could have done like kill %5. That would have killed job 5. I could have foregrounded job 3, you know, whatever. So you just give the job number. The percent number notation is whatever the jobs table says it is. If we look, we now have all 10 of them. You can tell they were, anyway, that's just a little example of running multiple jobs at the same time. Let me kick that off again, just because that kind of happened fast. And let's look at like our top and stuff like that. So like if I kick those off and then immediately do top, now you'll see we are actually getting a lot running at the same time. You will in fact see CPU numbers over 100%. That's because sort is actually a multi-threaded program. 100% CPU, pretty much in all statistics monitoring programs, PS, top, whatever, 100% CPU means one core saturated. So a number over 100% means actually multiple cores must be involved. So actually some of our sorts there, we're actually able to get 3 cores running at the same time in one sort. So actually, if you look there, our total number of cores we were sucking up for a second there was actually pretty high. At the moment, we're down to 3 sorts left, and they're kind of using 1 core each. So that's kind of like we're down to 2 cores, 1 cores. Now we're using 0. Most of the time in our session today, we are using 0 cores because most of our session is a shell prompt waiting for us to tell it to do something. So at this moment, with me just like this hands off the keyboard and no jobs running in the background, this our current CPU usage on node 7361 is 0, right? So like that job resource thing, and when you do the QRSH, what does that mean, that 3 cores? That's not like you must be using exactly 3 cores at all time. It's a reservation. It says that you are expecting, on average, over the lifetime of this job, to use about 3 CPU cores on average. So for us, that means you got to take the zeros and then whatever. But if you look at this moment when we launched all 10 of these, let me do that again and look at top. A lot of those are 200%, 300%, and we've got like 10 of them running at once. What is that? Well, that's like 20, 30 cores, right? Now we're only doing this for like 15 seconds. And most of the time, as I say, our usage is 0. So our average usage is probably even under 3 in this whole session, right? So that's kind of okay.
Allocating this 3.
Yeah. So the 3 is this. The 3 is a hint to the scheduler, and you can violate that, right? I mean, it's not a hard requirement. Hopin could have been organized in a different way. They could have used Linux features like C groups and stuff, virtual machines. They could have, when they give you a session or a job starts, arranged for the operating system to sort of completely enforce all the rules absolutely perfectly, right? You essentially get like a little mini Linux computer of 3 cores and 12 gigs of RAM. And even if the rest of the node is empty, you can't use it, right? Instead, what they chose to do is a more lax enforcement, where the cores is advisory, and you're allowed to be a piggy or a bad faith actor or whatever, right? So your program could suck up more cores than it kind of was, the scheduler was told that it's going to use. If the node is empty, no harm. Nobody else was on the node. The problem comes if multiple piggies exceeding their requests all get scheduled on the same node, because then you're all not going to get what you asked for, right? If you've got 10 piggies that are all trying to use 30 cores, the machine physically has 30. Well, 300 cores would be needed for that to fly at full speed. You're not going to get full speed. You're going to get like a 10th speed at that point because you have to share the physical hardware that's there. So the cores thing is more advisory. It's like you need to, you try to get it right because that's a good citizen. And it also kind of helps the scheduler put you in a place where probably you will get that. But if the Hoffman Q user base was all full of bad actors, it wouldn't work very well. But that's how it goes. So I mean, in general, it's a win because like if somebody has a job running they ask for 10 cores, but for half the time they're only using 5, there is this opportunity for you to burst and kind of take the stuff they're not using and stuff. But anyway, so it's a little tricky because every time in a shell pipeline you have a bunch of programs. Those are all possibly running in parallel. We saw that in our awk-based pipeline of fast-queue transformation, even though our pipeline had like 3 or 4 programs in it, it was mostly only using 1 CPU core. And that's because it was bottlenecked by the final gzip compressor. And gzip is a single core thing. Gzip will never use more than one core. It's a completely serial based program. It's just, it decompresses with one core, it compresses with one core. It decompresses fairly fast. It's not usually much of a problem in that mode, but compression is usually slow. And so gzip oftentimes, if in a bottleneck like in a pipeline like ours, it's the bottleneck. That pipeline, even though it had 3 or 4 programs in it, it could all be running in parallel. I think all the programs in that pipeline were single threaded programs, so they could use at most one core each. So it's conceivable that we could have been using 400 or 500% CPU, 4 or 5 cores in that pipeline. But in practice, that pipeline was just using 100% one core CPU because it was all bottlenecked by that last gzip. So it's not like there's a direct correlation between the number of programs in your pipeline and the number of cores they use. Number of cores you use can fluctuate over the running of a program. It's all kind of a complicated, slippery business, but basically, it's mostly the resource request is an advisory request. You try to get it about right, what your average usage is over the duration of the whole job. And the safe direction is to ask for more than you need, right? So I'm sure in this session, our average is less than 3. That's totally fine because we asked for 3. It would be worse if like we were running 20 core jobs completely saturated on this, then we just did not make a very good resource request. So anyway, that's how that works. While we're on the topic of sort of like how the resource requirements interact, the only hard enforcement on Hoffman is the time. Okay. So both in QRSH and QSub for jobs, that time number is absolutely enforced to the second. Okay. When your time limit expires, everything in that QRSH or QSub is going to die. And it gets killed pretty hard. It doesn't really even have much chance to clean up after itself. It's pretty hard limit, the time limit. The number of cores limit is kind of soft, like we just talked about. The RAM limit is also kind of soft. If you grossly violate it, the job system will kill it. But there's kind of a sloppy limit too. And it's kind of like, it's the limit is sort of imposed per process. And so it's not like the sum of all your processes is contained to that limit. Each individual process can hit that limit. So if you kick off like multiple copies of like an aligner or something in one job, each of them could be worked up to the limit that you gave it. And so their sum total could be vastly over. In that case, you should have made the request big. So the enforcement of the memory limits is also kind of complicated. We'll get more into that. But gross violations of the memory limit, the system will actually auto kill. But that's another case though where sort of like people can kind of be piggies and like not good citizens and lie, and so their resource requirements are less than the RAM they're really using, and that can contribute to this overloaded node phenomenon where sort of like you can get placed on a node where you were completely correct in your resource allocations, but somebody else lied and they really underspec the RAM that they're actually going to use, and they end up sucking up a lot more RAM than they asked for. And the scheduler has sort of arranged for that all the schedule jobs on that guy to fit in the RAM of that machine. But guy number 3 that it placed in the schedule is using 10 times the amount of RAM he should. And now the node is starved for RAM. And it could be trying to use virtual memory to kind of like page RAM. And it's dealing with a low RAM situation. And in that case, like the Linux out of memory killer can activate. It can actually decide to kill you instead of him. All kinds of weird things can happen. So even if, for example, you vastly over spec your jobs for resources, it does not guarantee that your jobs will actually all complete and get those resources. And this is also why when we get to day like 3 or day 2, and we start running dozens to hundreds to thousands of jobs, there is always the chance that those fail. And you must inspect the outputs, find the ones that fail, reruns the ones that fail until you get all parts succeeded. You can never just assume it's all going to work. You must deal with failures. The failures are stochastic. They're not all in your control. It depends on other people too, and so on. And that's one of the things that makes all this business complicated. And we'll talk about tomorrow. Anyway, let's take another 5-minute break, and then we'll last hour for today. How are we doing online? Everything still good?
Yeah, everything's good, Sean.
Okay,
Was just about to take the break.
okay, just let me know if you got any questions or anything.
Sure. Thank you.
Just to show you, here is my local machine. And I could just do a little. And there's exactly the same thing on my local machine as you saw on Hoffman, because it's a BSD Unix Mac OS. So it just works exactly the same way. Can kill individual of these guys, kill a bunch of them, foreground one of them, control C one of them once they're in the foreground. It's exactly the same. All the rest of it to top. That's the processes on my local machine. Actually, these days, operating systems on desktop operating systems are crazy. Like this Mac's got 700 processes almost, 3,000 threads. It's nuts how many background programs are running on a modern operating system these days. PS works the same way too. You can see all the processes. Everything we showed on the slides, the last few slides, all works just the same on the local machine.
Hey, Sean.
Yes.
Does the next part involve any hands-on
You
coding on
should,
my end?
uh, I mean, you can, we won't, everything we do in bisulfite alignment we'll redo tomorrow.
Okay.
So that's okay. The rest of it is just, you can follow anytime you like. I mean, you have the slides and the copy and paste thing.
Yeah. Yeah.
To your interest, you can follow along. Or if you need to be away from the keyboard or something, that's okay too. I mean, whatever works for you.
Yeah, I think I'll need to be away from the keyboard. So I'll just listen to what you have to say and then probably follow along tomorrow.
Yep, that should be okay. Because in terms of the bisulfite alignment task, where we need to end up, ideally where we end up today is to get the aligner installed and working and just to run one part, just to
Okay.
kind of show that it works. But in terms of requirements for making tomorrow work, there's none of the files we make in the next hour will be required as a dependency for what we do on tomorrow.
Got it. So I'll probably log off from my laptop and join on my phone.
Oh, okay. Yeah, that should be
Yeah.
okay. Also, uh, I, you get, even if you need them today, you can do it. So we're Zoom recording this to cloud, and then Eloy gets it, and then he can make the link available to you. So usually he sends out the links for all 3 days at the end of the workshop. But if you needed a video recording of a day at the end of that day, you can ask for that too.
I see. I see. Yeah. So I'll probably log off then
Okay.
and get the recording from Eloy.
Okay. Yeah, that should be fine. You should be able to drop your laptop Zoom connection, reconnect on phone. Uh, there's no, there's nothing about the Zoom thing that requires you to only connect once or something, right? It's just,
Yeah. Yeah. Right. I'll see
okay.
you in a bit.
We'll
Yeah.
see you tomorrow then.
Yeah. Thank you. Thank you, Sean.
No
Bye.
problem. Bye. Yeah, I can clean up a little here because finish today like this. Okay. So you heard what I said. Um, the most important thing to do if you're not going to be in the next hour is to try to get bisulfite bolt installed. So that is the last few slides. When we get to here, so these commands here, and if those don't work, you can try these, but I'm pretty sure this is going to work. This gets the aligner installed for you. It's a Python program, so it needs to be installed. So we make a virtual environment. We have to load the right stuff, make a virtual environment, and then install the right Python package. So it would be good if you could get bisulfite working. All you need to do is get to the point where if you say BS bolt, like you see the command, like it runs. You don't have to do anything with it. We'll do day 2. We'll do stuff with it, but it will save some time if you already have a functioning aligner tomorrow.
Okay.
But the rest you heard me say. So you've got the slides, you've got the copy and paste file. You can ask Eloy for the video recording from today, even at 6 p.m. or whatever. You could ask for the video recording from today.
Okay. Thank you so much.
Okay. Okay. Okay, so let's continue. This purple stuff is not so important. It's just sort of like an aside to be careful in certain situations. The only disadvantage of using file names with leading zeros in them is that you will at some point maybe do arithmetic on numbers with leading zeros in them. And that's a little dangerous because some software, for reasons I don't want to get into, but it goes back to the 60s, basically, 1960s, when octal was a lot more important. Some software interprets numbers that have leading zeros in them as a base 8 and not base 10. The shell is one of them. So I showed you shell arithmetic. So for example, here's 42 times 10 plus 7, whatever, 427, right? Shell arithmetic. The shell is one of those programs where if you put a leading zero on a number, it interprets it in base 8. So you may think that should be 11 because that's when base 10, that's 11. However, if 0, 1, 0 is interpreted as a base 8 number, that is a 1 in the 8th place. And so this number is now 8, right? And so 8 plus 1 is 9. And that is indeed the way the shell does it. Leading zeros activate octal in shell arithmetic. That is a surprise if you're not expecting it. And some software does that, some doesn't. So I mean, if you kind of even want an even worse example, what does this do? Well, the leading zero activates octal, but octal only uses digits 0 to 7, just like decimal base 10 only uses digits 0 to 9. 8 is not an octal digit. So that is not anything. That is an error, right? That is a, yeah. So
Not even consider it as 0.
That's not an octal number, and you asked for an octal number. So other programs act differently. So for example, we used awk a little bit. You can also do arithmetic in awk. And awk is an interesting case because awk even handles it differently depending on whether the number comes from the input data or whether the number is a number inside the awk code. So if I do echo O10 pipe to awk, this blob of awk is awk code that runs when awk starts up. This blob of code is that runs once per input line. So this is going to happen as soon as awk starts, and then the O10 is going to be the O10 is going to go to this block, which is the per input line block. And you see what happened here is that the first 9 comes from the begin block. And so actually this O10 plus 1 came out as 9. So clearly numbers with a leading 0 that are inside the awk code are treated as octal. However, the O10 that got pumped into this thing, where the print it says take the entire line and add 1 to it. That the $0 refers to the entire input line. So this is O10 plus 1. That comes out as 11. So actually on the input data side, they're interpreted still as in decimal. But in the opcode side, they're interpreted as octal. That's even like schizophrenic a little bit. That's even more surprising. What's even worse is that it depends on which awk you're using. So on Hoffman, it's GNU awk 402. For example, on Mac OS, the default awk is traditional awk 2020-0816. And if you can look at this, that's not important. Like I said, I don't want to spend the time, but if you look, these vary. So it depends on which awk. If you put the -- traditional option to GNU awk, you activate a different kind of handling. So it's chaos. And then if you look also, actually awk handles the 08 differently. So it interprets the 08. If it sees a leading 0, but the number can't be octal because it has digits 8 or 9, it goes back and interprets it as decimal. It gives up on octal and says you must mean decimal. That's kind of even worse. Now whether it's interpreted as octal or decimal depends on the number. Even leading zeros isn't even enough to activate it uniformly. So all kinds of minefields there with numbers with leading zeros. This little purple box also bothers to explain what shell arithmetic is these days. On most platforms you're going to be on right now, shell arithmetic is 64-bit signed 2's complement, integer arithmetic. So that means that if you get to like numbers like 2 to the power 63 size or more, things start to wrap around. So like if you start adding 1 to this number, you actually get minus the biggest number. Or if you take the minus biggest number and do -1, you back up to the plus most positive number. That's the usual thing with 2's complement arithmetic. A lot of computer languages work like that. And we won't need it, but sometimes in shell, you actually need floating point or decimal arithmetic. The shell can't do that itself, but there is the BC and DC calculator programs, and they are happy to take arithmetic expressions as a standard input and spit out decimals on standard output. And that is essentially a way you can do arithmetic, floating point arithmetic and shell scripts and stuff like that. Oh, what went wrong there? Anyway, if you take that away, it'll certainly work. It just won't, whatever, whatever. Not that big a deal. Anyway, just some minor points there. Let's see, we've got 40 minutes. Let me just see what's most important to cover. Okay. Maybe we won't get to installing BS Bolt, but maybe that's good because we got 2 people that are not able to be here with the last hour. So maybe I will decide that we will aim not to get bisulfite bolt installed and do that tomorrow so that everybody can do it together. And that means our aim is to reach this slide. And oh, I lied too. We actually need to do the split into pieces, which is needed for tomorrow. So yeah, so the guys that are missing this last hour they have 2 things to deal with, but this I kind of do want to do today. We'll work it out with them tomorrow, but I'll definitely, I think, kick off the installing BS Bolt to tomorrow. And yeah, we can probably do this in 40 minutes. Okay. All right. We haven't done anything useful with multiple jobs yet. We've just done sort of little toy examples. And so let's do something useful with them, something more realistic as a demo. So a very common thing one finds one has to do is gzip a lot of files. Okay. So how does that look like? Let's do these stupid little random files we made. They've got some size enough that they're not like just like tiny, I mean, they're not huge, but they're half a gig total. All right, they have some size. So we got these little random text files that we made as our demo a second ago. They have contents that look like this. They should actually be highly compressible because they only involve the digits 0 to 9, not full bytes 0 to 255. So they're probably pretty compressible. Let's compress them. So one option is to just give a single gzip command that just gzip them all at once. So you've probably given a command like this before. So maybe you don't do this, you just say this. So you can give gzip multiple files and it will gzip them all. However, it gzips them one at a time, one after the other. and it only uses a single CPU core for each gzip. You may be familiar with the -s best to work harder and make the file smaller, or the -s fast to work faster and get less compression out of it. But maybe you don't also know that -v verbose is useful in this mode because it will give you a line of progress as it finishes each file. So maybe if I do like gzip -v -s best and give it these 10 files, you will see here. So they're not, it doesn't take that long. These files aren't that big. Just pretend these files are even bigger. Okay, so it's getting a little slower because the files are getting bigger. But actually, you see we're saving half size on each of these files. And, all right, I'm going to Control-C that before that finishes. And you'll see here that we got 5 of them done. 6 was being compressed. gzip is pretty good though. Gzip, if you do a Control-C to gzip, gzip gets a chance to react to that, and gzip will clean up the partially gzip file that it made. So ideally, you don't end up with sort of inconsistent state. Either you got the original file, when you Control-Z a gzip, either you keep the original file, or if it made it to the end, you get the gzip file, but you don't end up with half the original file missing or half the intermediate compressed file that's only partially done still there. gzip tries to clean up when it gets interrupted. Okay, so what we could do, we already know, all we could do, we could do a for loop. All right, so if I do a for loop like this, okay, that would do 1 command per file. So I could do all the gzips in parallel, right? So I could do, instead of the echo, I will just do the gzip, and I will put that gzip in the background. Okay. Let me do it like the slide on 3 lines. That'll be easier. Otherwise, I have to explain to you the rules about shell punctuation with packing everything under 1 line. The only surprise is that you don't need the semicolon after the ampersand. The ampersand plays the role of the semicolon if you're going to pack it all to 1 line, but don't worry about that. So that's just putting it on 3 lines. It's easier to understand. So I'm going to hit enter, and you will see here that now, because my shell pattern was .txt, the ones that were already gzipped don't qualify to match the pattern. So we only started 5 because there were only 5 that weren't done yet. That's why we only got 5 jobs. And I actually kept the -v on the gzip. So you actually saw something kind of weird that we haven't seen before. So I got my shell prompt back because everything was in the background. This shell prompt is the shell prompt coming back after the final done of the for loop finished all its iterations. But you saw that I didn't type anything in between, right? My hands were off the keyboard there. But because the gzips eventually finished before I gave my next command, but because the -v has gzip right to the terminal, they actually wrote to the terminal while the shell was asking for a shell input, right? So the shell is still, this is still cursor, if you like, still sitting at the end of this shell prompt here. The next thing I type is going to the shell. It's just that we have several programs talking to our terminal at the same time now here. And the way it works is just that as each program writes to the terminal, it just goes to the terminal. So you get this intermix now of different programs running there. So you saw here that the way the gzip -v works is that it prints the file name, and then there's a delay. And then when it finishes the gzipping, it prints the other half of that line. But that's why, sort of like when we ran them all at the same time in the background, these are 5 lines printed by 5 gzips all at the same time, but they're all half lines that don't have returns at the end of them. So they all stack up like this. And then these 5 lines are the other half of those lines printed by those gzips. And the pairing is now kind of lost, but luckily gzip puts the file name in both the first half and the second half. So even though these could sort of be mixed, it's still sort of clear that this % belongs with this file because gzip puts the file name again. So that's okay. But I could hit return here, and you'll now see that shell will inform us that all of the jobs are done and our jobs table is empty. Okay, I'm gonna do that again. Well, I want to do this a few times so that I can show you a few things, but we have to alternate between gzipping and ungzipping because now all the files are gzipped already. So either I should ungzip the files and then I can do the same direction that I've already done, or we'll just bounce back and forth between ungzipping them and gzipping them just so that we can do a bunch of loops with multiple jobs at the same time. But since we're doing gzip, we have to alternate between the compressed and uncompressed, and we just did compressed, so our next one will be an uncompressed. Okay, so what if, okay, so we could do all the uncompresses in parallel, right? So we could do for X in rand star dot gz, do gunzip, verbose or not, right? Maybe I won't do verbose this time. So there, and then I will do ampersand to put those in the background and done. Now I'll get 10 of them, right? So because there's 10 now qualify in this for loop. So there they are. If I do an ls quickly, oh, wasn't fast enough. Some of them have already finished. Unzip is fast. Okay, so we didn't really catch the intermediate stage there. Okay, so we're back to, we got to do another. Actually, you see here, actually, when I did up arrow to get back to the pipeline, the shell already rewrote it, so it's all in one line. That's the shell. That's fine. This is completely equivalent to the 3-line format. The only trick here is that whereas you're kind of used to this, the ampersand counts as a shell terminator. So you don't do this. This is not right. The ampersand already counts as the semicolon kind of. So we got to gzip again because we're doing we've ungzipped now. Let me see if I can catch them in the middle. So nothing. Oh yeah, because the pattern also has to change because now they're .txt and not gz. Okay, now we got 10 of them running. Quickly look at it. There you see all 10 of them being built at the same time. Okay, and there you see some of them done, some of them not, and now they're all done. Okay. What if you have, let me unzip them all again. That's a serial version, but the unzip is so fast, it's less of a problem. Okay, now we're back to the original state again. What if you have a bunch of jobs in progress and in your shell script or something, interactively, it's not that big of a deal, but in a shell script, the shell script might start a bunch of jobs, but then it needs the stuff after that to happen only after all the jobs are finished. How do you do that? So that is what the wait command is for in the shell. So here I will get 10 of them going. They're running. Suppose I now need the rest of this after this to wait until they're all finished. So I say wait, and that means the job table must become empty before the next shell command can happen. That's a pause. So you saw here, I didn't get my shell prompt back until all 10 of them were done. If it was a little longer, it'd be a little easier, but I'm not sure you caught it. Let me do it again in case you didn't catch it. Okay. So this is the loop to compress them. We're going to get 10 jobs, and I will very quickly say wait, and you will see that I will not get my shell prompt back until all 10 are done. That's useful in shell scripts because you may have a part of a shell script that kicks off a bunch in background, but then you need the next part of the shell script to only happen after all that stuff finishes. So you put the wait in there as a barrier. If you need to wait for a single job, you can do that. Like you can do that. If you have the shell, if I do wait and no jobs, the shell knows there's nothing to wait. So that sleep is a 6,000 second sleep. That's like a long time. That's going to take a while. If I wait for that, that's a long time to wait. However, if you do Control C in a wait, that kills the wait early. So my job isn't dead. That is a Control C to wait, not a Control C to anything else. So that is how you interrupt a wait that you accidentally did or is taking too long or something. And then this job I can then kill manually. Why are you taking so long to kill that? Hello? Hello? Maybe this is a good time to tell you about the stronger form of kill. So the default kill, like you saw that gzip does a cleanup. When you tell gzip like Control C and stuff, gzip gets a chance to clean up its intermediate files and stuff. The normal kills and Control Cs and stuff like that allow the programs to interact. If you get in situations where apparently this is one of them, I don't know why, you may need a stronger kill that just says program die and you don't get a chance to do anything. So that you can say kill takes signals. These are all the standard Unix signals. The default one is sigterm, but sigkill is stronger. Sigkill does not allow the process a chance to respond. Yeah. Is it really there? Oh, finally. Okay, finally. It died. I don't really know which kill did it, but the kill is the strong one. If there is one that's going to work, that's the one that's going to work. Okay, so let me show you. So here's the problem that can happen once you start doing a lot of backgrounding. You can get stuff out of control, right? Because like suppose you had 1,000 files to use it, and all of a sudden now you've got 1,000 jobs running at once, but you don't have a 1,000 core computer. And now your machine is very slow because it's trying to simultaneously slice them. You can get problems where you made a boo-boo and now you've got too much stuff running and you need to like, how do I recover from an accident, right? So like here, I will start 30 jobs that are each sleeping 10,000 seconds. Given our experience with that last guy, maybe this is not a great idea, but there I have 30 jobs that are all long running. And oh boy, like, okay, suppose I need, how do I kill all this stuff? Okay, so you could do the very painful way, right? So you could do this. That will work. Okay. Why are only 21 of them dead? What? Why? Why are those other, huh? I've not seen it. The computer, they always know when they're being done as a demo. I've never seen it do this. And when I did it yesterday, it was fine. Very, very strange. Well, now it's a good time to tell you about the other way. The other way to do that is use the shell expansion as your friend, right? You don't want to type 1 to 30, right? So you can use the shell expansion to help you out. So here I've got 22 to 30 that are being sticky. Let's get it right. That should help. I could increase, hello. That's weird. I'm sure it's some strange thing with sleep. If I use some normal command, that probably would work better. But this is bizarre to me. I've never seen it do this. Yeah, whatever. Okay, eventually they go. But the point here is just to show you how do you do mass kills, right? So it's basically you can use the shell brace expansion to help you out. Um, this is another form, like if you've got pipelines that are going on with, these are simple commands, but if you have long, complicated pipelines, this next stuff, which I won't bother to explain, but basically like these are all the process group leaders in all the running pipelines. Like when you do PS, there are these process IDs, which are what the operating system really understands. So these are like all these are all the numbers of all the jobs that are running in terms of the operating system. And then we can kind of use some shell magic to kind of capture those in a shell variable and then add a minus sign in front of them, because a minus sign is when you give a minus sign to the kill command, that means kill the whole process group and not just the single process ID. And so if we replace that echo with a kill, this is basically, you can just take this as sort of a magic line, but this basically kills everything in the job table. Notice that the mass kills I did so far, I had to know the job numbers. Like I used %1 to 30 or whatever. It's been a while, but how far back do we got to go? But here I had to know the job numbers. Like, what if you just want to kill everything and I don't? You've got some weird subset of number, which just kill it all, right? So basically, this is sort of a magic command line that sort of figures out all the right numbers and then sends them to kill. And that kills everything without having to keep track of what the numbers are. Although, for whatever reason, I've got these sticky sleeps that I don't understand. But this is sort of a kill everything in the job table. You may reach situations where that's not enough. Like your shell is like, you've made a real mistake and now like you want to kill everything on the node, right? Like every job I have, every process I have in this node needs to go, right? Like total reset, panic button, emergency stop. So what I'm going to show you though will kill everything on the node that's yours. So that means that's going to kill your session on the node, because we're going to kill the SSHD process and we're going to kill the bash. So that your session's going to blow up. If you had other sessions onto this node or other queued jobs that happen to land on the same node, they're going to go to. We're blowing up every process we know we own on this node. Okay, so because I don't want you to lose your main session, don't try this out in your main session. Make a scratch session, QRSH to some random node, you know, maybe it's going to be 7361, and then we'll test out that it will blow up both sessions, but probably this is going to land on a different node than 7361, and then we're just going to blow up just the one here. So let's find out. That's like a QRSH with no like default parameters, like no resource requirements at all. Like it's like 1 core, 1 gig of RAM or something. Like, come on, Hoffman. That's like the easiest ever. Anytime.
I have an unrelated question.
Okay.
So when you are compressing, is there a way to control how much you're compressing? Like, is it 10% of the original?
Oh, no, that's not. It's a lossless compression, so it's up to the algorithm to do what it can, and the algorithm will always do at most it can. There usually is a trade-off between how much CPU time it spends to how good of a job it can do. But you can't say compress. You can't give it a random file and say compress to 1% of its size and expect it to be lossless in every situation, right? Just the mathematical pigeonhole principle says that's impossible, right? You cannot take all binary strings of length 100 and reduce them to binary strings of length 20. Pigeonhole principle says at least 2 of the inputs have to go to the same output. So just because there's more inputs than outputs, so that can't be lossless. Okay, so here we go. We're on node 73. Oh no, we're on node 7361. It's the same one. So do I want to do let's prove the point. Okay, so the real one here is kill all. Okay, kill all -u cocos, or if you want to use the shell variable to make it adapt to yourself, right? So that kill everything owned by user this, and then implicitly that is on this machine. That's not like a queue system thing. That's a node that's to the node. So when I do this, I'm going to lose this session, and I'm going to lose my session on the other window too, because it's all going to go. Boom. Okay. So you saw this guy died too. That is the emergency stop if you're in a bad situation. When you do this, you also are probably only doing this because things are out of control. You've got hundreds of processes or something happened really weird on the node or something. In this case, this is the one time you may be allowed to sort of directly SSH to a node. I want to see that all my processes are gone on that node. I want to verify that my cleanup was successful. So I am going to get a complete listing of all processes on that node and then pipe that to grep and grep out my username, or like this, and just see what comes back. And I'm expecting to see basically only the SSH, only this SSH, and this grep actually happens on my local machine. This SSH and this PS are the only processes I expect to see when I do this momentary SSH to run this PS command on that node. This is just to verify that everything is completely cleaned up, and it is. You don't see any bashes, you don't see any sleeps, everything's gone, right? So this is just to verify that I cleaned up myself on that node correctly. You should never ever directly SSH into nodes and circumvent the job queue system. You should always QRSH or QSub to do all your actions on compute nodes. This is kind of the one time that sort of maybe I'd say it's allowed because you're trying to verify that you cleaned up some kind of accident that you had. Yeah, so that's the panic button, but you try not to do that. Yeah, your question about sort of compression though, there is like I'll show you here. So Z standard from Facebook is an alternative to gzip. It has a lot more knobs for how you control the trade-off between CPU time and compression time. And like, for example, here I'll ask it to benchmark itself from compression level 1 to compression level 19. And it's better if you actually use the benchmark on files that are relevant to you, because how they compress depends upon the particulars of the file. Here it's using a made up text file that it uses as just a standard if you don't specify otherwise. But here you're seeing at compression level 1, it made it 3 times smaller, and it was compressing at a rate of 400 megabytes a second, and it's decompressing at a rate of 650 megabytes a second. At compression level 3, it's achieving 3.4-fold decrease, but you see the compression speed is going down. The decompression speed, like gzip, is more constant. Z standard is a near constant time decompressor, like gzip, but the compression levels are more about the compression time trade-off. So here you see the compression ratio is getting better, but you see our compression speed is dropping. So depending on whether the file you're compressing is designed for long-term storage, where maybe it's worth it to spend more time to compress it because disk space is precious. Or if it's an intermediate stage in some pipeline where you've got some big pipeline, you're making a big intermediate file. The only purpose of this intermediate file is to save disk space in the middle of the pipeline. It's not going to be a long-lived file. Then it makes sense to use one of the lower compression levels so that the compression can happen fast. You don't want to, you're just trying to use the compression to save some disk space in the middle of the pipeline, not, you don't really want to use a lot of CPU time if you have to in that stage. So then it makes sense to choose one of the lower levels of compression that compress much faster. But you see quite a range here. We're now at compression level 13, but our compression speed is 3 megabytes a second. That's 100 times slower than compression level 1. But the ratio is it's almost up to 4. Yeah, there it goes, 4-fold smush of the file there. So it's now achieving. But you see, it's a kind of a, usually it's a, what do you call it, diminishing returns kind of business, right? So it's not like the file is like continuing to shrink by great amounts. We're going from 3-fold division to 4-fold division, but our CPU speed is changing by a factor of 100. It's actually changing by 300 now, right? We're now down to like 1 megabyte a second compression. You see the decompression is still fast, 600 megabytes a second. Right, I don't know if we'll let it go to number 18 there. It actually is eking out more lossless compressions. It's up to 4.3-fold, but we're down to 1 megabyte a second, which is very, very different than, so I don't know. So level 2 wasn't that bad, right? Level 2 is almost as fast as level 1, and it's 3.2-fold. The next batch would be maybe like level 4. That's almost as fast as level 3, right? But actually, I mean, pretty much every level is a step down here. I mean, it's pretty substantial. gzip also has compression levels 1 to 9. Fast is -1, best is -9. The default might be like 4 or something, whatever. But anyway, all compression programs have these kind of trade-offs. Okay. So, okay. Well, we're going to get to where we get. I mean, like I say, I'm not too worried because day 3 is only partially filled, and if we spill into it, that's no problem. We'll just take whatever time we need. One of the things I mentioned, oh, I did that on the login node. That was probably a bad idea because that was actually working a little, So let's see. So I don't think I need heavy RAM or cores right now, so I'm not even going to bother to give the same resource requirements for QRSH that I did at the beginning. Since I lost my session, right? The kill all blew up everything, right? Because I randomly landed on the same node as my main session. So, and we decided to test that out, and it works. So I have no compute node session right now. So let's get back on a compute node because I apparently did this gzip test or this Z standard test on the login node. There we go. Okay, so we get back down into the directory where I was doing everything. Okay, that's here. All right. And yeah, let's do this little thing. This is sort of an independent little component. So yeah, one of the things, like when we were doing this pipeline, right? Like we were doing this this was our 18-hour guy that we were running near the beginning of today, right? And we've been interrupting him each time. And then we end up with this partial file. The problem is that the partial file is named exactly as like it just looks like an ordinary gzip file. And that's sort of not great. I mean, it's okay because we were the one that started this pipeline and we were running it interactively, and we were just sitting here waiting for it to finish, and we were the ones that hit Control-C. So obviously we know that we interrupted it and the file is partial. However, if this was in the middle of some pipeline, in the middle of a shell script, in the middle of a queue job, sitting in a pile of 1,000 other queue jobs, well, now if it dies in the middle, it's less obvious because now it's mixed in and it's a needle in a haystack. So it would be nice if, for example, while files were not complete, they were named in some way that made it obvious they're not complete. And then only after things are finished do they get renamed so that they look like they're complete. So that's this little kind of shell pattern that I'll show you down here, which we will use on and off. I mean, we won't use it every time because it kind of reduces clarity a little bit. And some of our things as you're learning are already opaque enough. But in some of our shell scripts and stuff, we will follow this pattern because it does help you when you start doing lots of jobs to have all the help you can get to decide whether a subjob completed or not successfully. So here's the idea. I don't want to do this guy as an example. That's too long of a command line. And so let's do a simpler, just toy example to kind of see the pattern that I'm talking about here. So, okay, so here's this little line, shell line. And what is this? So these parentheses make a little subshell. So another shell is going to start, and that little shell's job is to run these three commands, which are basically just to print out the date, wait 1 minute, and then print out the date again. So that just produces some output and takes 60 seconds to produce some output. So it acts like a little mini job. We wrap that up in parentheses and then do a shell redirection. So we capture that output to a file. The parentheses mean that we capture to the file the output of all three of these in a row, right? If I did not have the parentheses here, only the final date would get the redirection. So this just groups the redirection so that it applies to all three of these guys. The new thing is that instead of like a semicolon or an ampersand for background, I now have two ampersands in a row. So that is what's the new thing is and what will require explanation. And then you see an MV command here to do a renaming. So the idea is, okay, here's the thing that's producing output or whatever, and this is the output file name. So the idea is this is kind of the file name you wanted to give it. But the pattern is put something in the file name that makes it really obvious that it's not done yet. Okay, like in progress, whatever. Then after this is successful, do an MV command to rename it so that you remove the little indicator tag that says that it was successful. Okay, that's the pattern here. Let's get it all on one line. Okay, so I want to play with this as it runs. So well, let's run it not in the background first. Okay, so I'm going to run this whole line. It's going to take 60 seconds to run, of course, because it's got that sleep in there. So, okay, so I hit enter and it's running, but maybe I interrupt it. Okay, so I'm going to control C it. Okay, so it didn't get a chance to finish. Now, pretty obviously, the file name is going to be the one within progress at this point, right? Because the MV comes after this thing, and this thing takes 60 seconds to happen, and I didn't wait 60 seconds, and I aborted it. So very unlikely that this MV command ran, and indeed, that looks like the situation, right? So here is the example of the pipeline not running to completion, and you see the file name is kind of marked that way, okay? Let me reduce the sleep to 10 seconds so that we don't, let's just do 5 seconds. Okay, so let's reduce the sleep to 5 seconds and let the whole thing run and see what happens, okay? Okay, so, and you see MV with the V is verbose for MV. MV with dash V will actually show you a line when MV does the rename from to. The F is a force. It means that if the destination already exists, then overwrite it. So it looks like the MV ran, and now indeed, if I look at the file name, actually it does not have the in progress tag. And if I look at it, it's got the two date lines in it. So that's the kind of behavior that we like. Now you may ask, okay, well, what's the double ampersand for? Why not just put a semicolon there? Well, interactively, that may not make much difference, but in a shell script, there's a big difference. So if this was a semicolon, or if you had just simply put the two on separate lines, so like you just did this, and then you have the MV on a second line like this, okay? Or I'm talking about the other alternative is if you just put a semicolon here instead of a double ampersand. The problem in that case is that there is no decision about whether the first part of it was successful or not. I mean, the control C is sort of a different story. The control C is killing everything, but suppose this program had an error in it, right? But it wasn't like control C from the outside. It just didn't work or something, right? Maybe you got the syntax wrong or something, right? You know, whatever, command line options wrong, or input file didn't exist or something. So the problem is that the semicolon and putting lines on different lines, the way the shell is written to work is that those situations, the second command always runs regardless of whether the first command succeeded or not. And that's not what we want to happen. We want the second command, the MV, to only run if the first command succeeded. So we haven't really talked about what succeed means. And usually even in workshop 1A and 1B, we don't even get to it. But basically every program on Unix always returns a return value to the caller. It's a small integer. It's just an integer from 0 to 255. So there's this secret sort of return value that every program, date, sleep, cat, awk, they all do. Every program has to return a number to its caller. And it's just a small integer. And the convention is, the universal convention in Unix is 0 means success, non-zero means failure. And if the program is written to follow that convention, it means that the caller of the program can use that return value to conclude whether the subprogram succeeded or not. All of the standard utilities, date, cat, dates, how's date going to fail? If you're clever enough, you can make date fail, but don't worry about it. But like cat, you could ask cat to cat a non-existent file, right? Or something, or sort could run out of temporary disk space. Like you hit your quota. If you're sorting a huge file and sort has to make temporary files, you could run out of quota or something. So programs can fail. All the standard utilities are extremely good about the exit value being 0 for success, non-zero for anything that you might reasonably be considered a problem. Other software like academic software, like our Boat one, it's a little iffier, and we'll talk about that tomorrow. But certainly for all the standard utilities, it's true. So the difference between the semicolon and the double ampersand is that the double ampersand pays attention to the return values. The double ampersand runs the thing to the left first. And if the exit status of the thing to the left is 0, it runs the thing to the right. And if the exit status of the thing to the left is not 0, it does not run the thing to the right. So we are conditioning the running of MV on a 0 return status from the left-hand side. So that the left-hand side, the MV only happens if the left-hand side is a success, as defined by the programs in the left-hand side. So that is the way that we make the rename only happen during a success. So we'll see that pattern used in some of our scripts and so on tomorrow. The shell actually makes the exit value of the previous command available in $? So if I run a command, like if I do cat like ex1 out txt, that's a success, right? That will work. And if I ask the shell, what is the exit status of the previous command? I get a 0. But if I ask cat to say some file that doesn't exist, and cat gave me an error message, and I asked the shell, what was the exit status of the previous program? 1. So that is a way that a script or something can use to tell whether the cat, whatever command it just started, did that work or not, or did that reach some error message? That is the mechanism by which that's done. And the double ampersand is the easiest way to make use of that. Double ampersand is like a semicolon, but it's conditioned on, it only does the right-hand side if the left-hand side succeeded, where semicolon always does the right-hand side. Okay, so we're pretty much out of time. And where are we headed? Well, okay, this is good because we didn't get to the split yet. And the people that aren't here for this hour, that's good because otherwise they would have missed the split too. So this is a good place to stop anyway because it'll let us sync up everybody again tomorrow. So anyway, so that's where we are. So we're at the slide 32 here in day 1 slides. Okay, so we will need more slides than I've currently distributed. So you'll get another PDF file tomorrow and another copy paste file tomorrow, because we will in the first hour tomorrow run out of slides from this batch, but that's where we are. Okay, so I'm going to stop the recording.